Hello, everyone. It's a great pleasure to start the last day of the School of Electrochemistry. This will be a different day. We will have some lectures, Metrohm Autolab presentation, and some other in the last presentation we have a research presentation. And to start the day, we have the Victor's lecture. Victor will talk about the energy storage, and Vitor will talk about a little bit about this, some research and about some other topics related to the energy storage. Vitor was already introduced in the first day, and we return here today in the last day. Thank you very much, Vitor, to come, and the stage is yours now. If you'd like to share your screen, it's with you. Thank you very much, Vitor.
Thank you, Thiago. Hello, everyone. Good day to everybody. So you are seeing my screen now, right?
Yes, you only need to put in the full mode. Yes, perfect.
Okay. All right. So this morning, this first hour, we have some specific topics, right? And I will talk a little bit on energy storage. I give an introduction on energy storage, but today we will be thinking specifically on electrochemical energy storage, all right? And as an introduction, for a reason to be concerned on energy storage is just because we need to rethink the way that we consume energy and the way that we produce energy. And storing energy is a way to have a different grid of energy distribution, right? So first, you can see here on the left, this graph. We have different months on the circle, and as the time goes, here you have year, you can see the average temperature for that month. And as you go on in time, the average temperature is increasing. And the last one here is for 2016, almost 1.5 degrees higher than the average 2 centuries ago, right? So here's another figure or graph showing the average temperature in the globe. So the red line is the temperature, and the yellow line here is the solar activity, right? So irradiation. This is just to show you that the increase in temperature is not related with the activity of the sun. So it is related with the activity of the humankind, right? So we need to rethink the way we produce and use energy. There are a lot of promising technologies, for example, solar and wind. Those technologies are already well established. It's used in a lot of places around the globe. But the problem that everyone knows about those technologies that they don't produce the full time, right? So the sun only radiates during the day. There's some time that we don't have that much of wind. And then the idea is to store this energy that is produced to be used when needed. So here's an example of a big battery storing this energy that's produced by the wind here. And then when the wind stops, you can use the energy that was stored in the battery. All right, so battery is not the only way to store energy. So as I said, the idea is to store energy to use when we need and we can produce. All right, so we can't produce energy all the time, but we can store the energy that was produced before. So we have different classes of technologies, mechanical, and then pumped hydropower. That's really common in Brazil. Almost a little bit more than 80% of the produced energy in Brazil comes from hydropower. And if you think of a hydropower plant, we always think of producing energy, but you can also pump the water from the river upward to the reservoirs. So you are using some energy to pump the water up the reservoir. So we are storing the energy in that way. So we have another technologies in the mechanical class. So we have electrical, like the physical capacitor. We'll talk a little bit later on capacitors. I also have thermal, storage, chemical, so fuel, biofuel, hydrogen, and then we have electrochemical, right? So we have fuel cells, then you have a mix of chemical and electrochemical in here, and then we have batteries and electrochemical capacitors. So today we will talk specifically on batteries and electrochemical capacitors. This graph here, it's the Ragon plot, and it shows the energy density of a device or a technology and the power density of this technology. So let's think a little bit about what is energy. So energy is the ability of a body to perform some work, right? And we have different types of energy. So we have kinetic energy that's related with movement of this body. And we have potential energy that's related with position in some fields. And then we have chemical energy that's related with the energy in the bonds of the molecules. And then the electrical energy is a type of potential energy, right? So it's the energy that a body related with the position of something in the field of electromagnetic field, right? So Energy is measured in joules, and joules can also be written in watt-hour. So watt-hour is the most common unity for energy in the field of electrochemical energy storage. Watt-hour is also amps volt-hour, all right? So watt is amp volt. And then power. So power is just the rate that we perform that work. So it's the rate that you use the energy, or the rate that will recharge a battery, for example. So if it's a rate, it will be energy over time. So you have joules per second, or just watt, right? So we have energy is watt-hour, and then the rate of watt-hour, that's power, would be just watt. So there's one thing that we need to think, is that we can calculate the instant power. So instant power will be the current times the voltage, or the potential, sorry. So I'm using V for potential here instead of E because of energy, right? So you see this in other slides too. So this is potential. And then current times potential will be amps times volts, that's equal to watt, as I said before. And this is the instant power. What we report normally in Raglan plots is an average power. And we'll talk a little bit later when I show you how to calculate energy and power density from some measurements, all right? So let's look to this Raglan plot here. The best situation is when we have things going up on this direction here. So, oh, sorry. And here we have the internal combustion engine. So it has a lot of energy density and a lot of power density. And on this corner here, we have the physical capacitor, so electrostatic capacitor. It doesn't store a lot of energy. Sorry, guys. It doesn't store a lot of capacity, but it can deliver a lot of power, right? And then we have fuel cells that doesn't have higher power, but store a lot of energy, and different type of batteries, and then the electrochemical capacitor. So let's think about this two here. The lithium-ion battery can store more energy than the electrochemical capacitor, but operates at a lower power than the electrochemical capacitor, all right? So you see why in the next slides. So as everyone knows, the Nobel Prize in Chemistry in 2019 was for the development of lithium-ion battery. And the prize was to Professor Goodenough, Professor Wittigan, and Professor Yoshino. And I will go through the development that those Nobel Prize awardees made for the lithium-ion battery development, right? First, Professor Wittigan introduced an intercalation compound, that is titanium disulfide, to be used as a cathode material. So he developed a cell, so electrochemical cell, using a metallic lithium as anode or negative electrode, and titanium disulfide as positive electrode, the cathode. And then you have here the electrolyte, that's organic solvent with some lithium salts on it. And the reaction going on these two electrodes will be the lithium reaction. So we have oxidation of lithium and then reduction of lithium during the battery operation. And you have the intercalation of lithium in the lithium disulfide compounds. So we have reversible intercalation of lithium during oxidation and reduction. So the interesting part here is the reversible intercalation and deintercalation of the lithium ion in this kind of compounds. All right. He got 2 volts of this battery. It's not that high, but was a really good start, right? You have a rechargeable battery using this system. Then the next step was done by Professor Goodenough, and he changed the positive electrode. He starts using another intercalation compound, but this time it was lithium cobalt oxide, or LCO. So the reaction on the negative electrode was the same, so lithium was used. And then we have the intercalation of lithium in the LCO electrode. This reaction was also reversible, so we could charge and discharge the battery a lot of times. And the nice thing of this compound is that the difference of potential between these 2 electrodes, or these 2 reactions, is 4 volts. So you increase from 2 volts to 4 volts, and then you gain a lot of energy and power density. The problem of this system is that using lithium, metallic lithium, you grow some dendrites during oxidation and reduction of lithium. Those dendrites grows through the cell and can go through the separator here and touch the other side of the cell. This will cause short circuit and can cause fire. All right. So this was a bottleneck of this technology. And Professor Yoshino made his contribution on this part. All right. So he changed the metallic lithium here in the negative electrode by graphite. So graphite is also an intercalating compound, so we can intercalate lithium and deintercalate lithium during the battery operation. The cathode material was still the same, LCO, and the interesting thing here is that you can use carbon or graphite in the negative electrode and keep 4 volts as in the previous system. So in this way, with this composition, graphite, LCO, organic solvents, and lithium salts, we have the first battery that Sony produced in the early 19. So this is the technology that is used a lot today yet. You have some increments as in the graphite electrode, as in LCO, have new materials like NMC. You can use nickel, manganese, and cobalt, because the idea is to increase the energy density of the system, right? So we'll see a little bit later on this. All right, so to sum up here, the development of the lithium-ion battery. In red, you have the reaction that was the main contribution of each of the awardees. So lithium disulfide here, LCO, so lithium cobalt oxide, and then the introduction of graphite in the negative electrode. And then we have this reversible battery with 4 volts. Let's think about some quantities in batteries, right? So normally you see some reports, or even when you are buying some battery, or when you are checking the specifications on a cell phone, for instance, you have capacity. And what is capacity? Capacity is just the same thing as charge, all right? So capacity is current times time. So we have amp hour. The difference of capacity and charge is just the time unit. So in capacity you have amp hour, and charge you have amp second, that's Coulomb, right? So we saw this, the Warwick charge. And capacity is a way to represent the charge of the battery. And then again, we have energy and power. Energy is just the potential times charge. So you have volts and hour or watt hour, as I said before. And then you have the instant power, that will be potential times current, that's volts amps, that's watts, right? Those three quantities are the main parameters that you see on a battery report. Of course, those are the battery performance parameters. You can look on fundamental of the battery. That's the important part of some research. But those are the performance parameters that we will find. And then I would like to move a little bit to electrochemical capacitors, right? So here is on the left, you have electrostatic capacitor. That's a physical capacitor. It's not the electrochemical type of capacitor. So I have two metal plates and a separator between those two plates. Those capacitors, those physical capacitors can be classified by the type of separator. So you can have vacuum, can be dielectric, or you can have some oxide film between those plates. The thing is that you can apply a difference of potential between those two plates, and electrical charge will be stored when you open the system here, the external system. The electrical charge will be stored on those plates. So one plate will be positively charged, so it has less electrons here, and the other plate will be negatively charged, it has excess of electrons. But as in the first class in this week, I said, so the capacitor in here will be with zero net charge, right? So those charges are cancel each other, and that's why you can open the external circuit and the charge will be held in those type of device. We have different materials over here, but the thing is that the energy of this device is proportional to the capacitance of stored here, and the voltage to the square square voltage here over 2. We will think a little bit on why over 2 here later. But the important thing here is that we can increase the energy of a system like that, increasing capacitance and especially increasing voltage. So capacitance is related with the area of the plate or of the electrode and the thickness or the distance between the plates, all right? So the thickness of the separator here. And we saw in the first class this week that we have electric double layer. The interesting thing of electrical double layer is that you can decrease a lot the thickness of this double layer. So we have the electrode as a giant ion here, negatively charged, and then we have the ions compensating this charge that will be positively charged, and then we have the thickness of this double layer. The thickness will go here. So as smaller the thickness, greater the capacitance will be. Greater the capacitance, greater the energy. And you can also think on the area of the electrodes. We have different types of materials used in electrochemical capacitors, but especially activated carbon have area range from 1,000 to 1,000 square meters per gram. And then you have the thickness of the double layer. And as you have two capacitors in series in a cell, you need to have two capacitors, right? So one electrode will be the positive and the other one will be the negative electrode. You have that the total capacitance of the of the device will be the sum of the inverses here, like I showed you in the first class. So that's how we increase the energy density of a capacitor using electrochemical capacitors, right? That's also known as supercapacitors, because we have a much greater area than the plates here and a much thinner thickness of the double layer. But we also can work with the voltage, and the voltage will depend on the material that we have between the two electrodes or the electrolyte. You'll see a little bit more later. And then we have also within the electrochemical capacitors two types of device. The double layer, that's the one that I told you in the previous slide. And then we have also pseudo capacitance. So the double layer is just related with the formation of the electric double layer. So there is no redox reaction here. We don't have electron transfer in the interface, right? So it's just a non-Faradaic process. But we also have some Faradaic process that show some properties of capacitance or capacitor. Those are fast superficial reaction, and they will show performance like a capacitor. So those are called pseudo-capacitance material. So here it's a class of material, the process related with this material, and some examples. So carbon have activated carbon, graphene, for instance, and they will be based on double layer process. Then you have some oxides, and then these oxides will have a Faradaic process that is a pseudo-capacitance process, and also have conducting polymer, and then we have also some pseudo-capacitance. It's a Faradaic process. So you have, in these two cases here, you have electron transferred in the interface, right? One thing to observe here is that it's really common for many years, people reporting materials that are Faradaic, but they don't show a pseudo-capacitance profile. So you can tell by electrochemical experiments if a material has a pseudo-capacitance process or not, right? So for instance, here in this first graph, you can see the peaks during the cyclic voltammetry. And on the right here, you have manganese oxide. And the whole process of the redox reactions of the manganese oxide is distributed in this potential window. And this is a profile that a capacitor has, right? Remember in the first class that I showed you that the current is constant during the cyclic voltammetry. And this is because the capacitance is constant during this potential window, right? So it's really easy to tell in those cases, but there are some cases that's more difficult because you have some waves, and then we need to think closer or a little bit more if it's if you can calculate the capacitance of this material or not. And one last message in this slide is that there is no such thing as pseudo capacitor. There is no device that is called pseudo capacitor, right? Pseudo capacitance is an electrochemical process that's related with the electrode material. So you can have pseudo capacitance in the electrode material, but then the device is called electrochemical capacitor. Okay, so there's no pseudo capacitor.
Sorry, Vitor.
Yeah.
Are you listening? Oh.
Yeah.
Rona asked a question here in the chat. It's about what is the energy capacity?
So energy, so capacity is charge, all right? And then energy is the ability to perform work. So there are different things, all right? So capacity is charge. Let me go back here. In here. So capacity is charge, is amps hour. And energy is in this case, is the electrical energy is potential times charge. All right. So this is the ability to perform work. So watts hour. And then the capacity is just the charge stored on this device. Okay. So there's no energy capacity, it's just or energy or capacity. Okay, so let's think on the difference of these two types of device and think on electrochemical methods that we can use to evaluate those materials or device, right? So here you have electrochemical capacitor on the left and some battery materials on the right, and the cyclic voltammetry of those different materials. The electrochemical capacitor here is activates carbon in one ionic liquid that doesn't matter now. And the battery show here, this graph shows different materials of batteries. And the first thing that you can see here is that during a cyclic voltammetry in capacitor or electrochemical capacitor, you have a constant current during the scan, right? So this is a typical capacitor being charged, like in the first class. And here you clearly see the redox peaks of the materials. For instance, you have LTO here, have a very clear peak of the oxidation and then reduction. And this is true for all those materials. So we have lithium here, and then have graphite, and this red here is the LCO, the first compound that Professor Goodenough reported. And the actual potential of the battery will depend on the combination of this material as cathode material and anode material. So negative electrode and positive electrode. The operating potential of the battery will be the difference of those redox process here. All right. So if you have LCO with graphite, you have that 4 volts. And if you have NMO with lithium, you have 4.5 volts, something like that. But then you can also have, for instance, LTO as negative electrode, and LTO operates close to 1.5 volts. And then you can match it with LFP, for example, and then LFP is close to 4 volts. And then the difference of this voltage here will be this potential will be the battery potential, right? Then you have galvanostat experiments of charge and discharge. So in this upper case here, you have potential statical regime. So you control potential and measure current. And this one here, you control current and measure potential, right? So you're applying a current and measure this potential. You see here, it's the same example on this electrochemical capacitor, but now we are applying different currents here, and then we can plot against the charge. Why charge? Well, charge is an easy way to compare materials, right? So this x-axis here is just time times the current that we are applying. So when we are measuring this kind of experiment, you are seeing the voltage variation in respect to time. But when we are plotting to compare with other things, you can multiply the time from the measurement with the current that we applied, right? And then we have a linear dependence of cell potential with time or charge being stored in the device. This is for a capacitor. But for a battery material, for a battery material, you have a different kind of profile. So we have discharge profiles here for those different materials. And see, you have a plateaus here. So LFP, you can see very well the 3.5 plateau here of LFP. That's why you, that's because you have redox reaction here that we don't have in the capacitor. So the redox reaction happened in that specific potential, right? So you don't have a variation of potential during this redox reaction. This is true for those materials here too. So we can clearly see the difference of electrochemical capacitors and battery operation. So why you have different energy stored in capacitors and batteries? So here it's a plot of potential during charge of a battery and a capacitor in function of total charge. So here you are charging the battery and the capacitor to the same charge and measure the voltage. So we are applying a current up to the total charge in measuring the potential of this device. As I said, the battery will show a plateau, so it's a line. The potential doesn't vary during the charge, but the capacitor does, right? So we have a slope here that's related with the capacitance. And then the voltage, the potential increase with the increment of charge in this capacitor. And I told you before that the energy, the total energy of a device will be the integral of voltage in function of the charge. And for the battery, that will be energy of battery in function of potential of battery. And the energy of the capacitor will be in function of the potential of the capacitor. But if you see here, the whole area underneath this line, this dotted line here, will be related to the energy of the battery. But for the capacitor, no. The capacitor you have only the area underneath this dashed line here. So we can say that the energy of the capacitor will be related with the energy of the battery divided by 2, right? Because this is half of this area here. And we also know that the voltage is equal to the capacity or the charge over capacitance. So if you make the units analysis here, you see that. And then charge will be potential times capacitance. And then we can write that the capacitor energy will be the potential of the capacitor times the charge. And that is this capacitor potential is the voltage, the total voltage divided by 2 because of this relationship here. And then we can exchange the capacity or charge here through this relationship. And then we have that the energy will be half the capacitance times the square voltage, as I told you a few slides before. And all those parameters that we have for energy, power, and cycle life for electrochemical capacitors and batteries are related with the process that are occurring in the device, right? So the energy that is stored in an electrochemical capacitor is much smaller than the energy stored in a battery, because the battery, you have redox electrodes. So we have a bulk electrode participating, the whole electrode is participating on the storing energy. But in the electrochemical capacitor, you have normally only the surface area of the electrode, right? So you have you don't have the bulk of the electrode participating on this energy storage. But that also impacts the power density of the device. So as in battery, we have this redox reaction, you are limiting the power of the device by the kinetics of that reaction. On the other hand, in electrochemical capacitor, the process is just superficial, it's just in the surface of the electrode, and it's really fast. So you have a much higher power density. And as in the electrochemical capacitor, you don't have a chemical reaction actually, so we don't have changes on the electrode, it's just superficial electric charge being stored in this electrode. You can cycle this device over thousands and thousands of cycles. In the case of batteries materials, you have the electrochemical reaction taking place in both electrodes, and those reactions normally change the volume of those materials, can have a phase change also of those materials during lithium intercalation and the intercalation. And those changes will impact the cycle life of those materials, all right? So remember that those performances here are related with the process that are occurring in the electrodes.
Sorry, Vitor, to interrupt you.
Okay.
We have a question here in the chat. Luis is asking about how can know the final time during discharge measure.
Okay, I will talk
each cycle. Yeah. Oh, perfect.
Yeah, I will talk a little bit this later. All right.
Okay, thank you.
So we have different types of cells to perform electrochemical experiments, right? So that's also true for energy storage experiment. So those types of cell here, that's really common in electrochemical labs, is just to start to investigate a new material. So preparing an electrode for drop casting of a really small quantity that we can't really measure the amount of mass of the electrode, is just to have an idea of how that material work in that electrolyte. So we have a lot of electrolytes here, just as really small amounts of active material is not ideal, right? So it's really far from applicability. Then we have another type of 3 electrode cell that's type Swadlock T. So we have electrodes inside the Swadlock here. So we have the working electrode, the counter electrode, and then we have separator, and we can use a reference electrode between them. You have separators, can be glass fiber or some polymers, and you add the electrolyte here. This type of cell is good to measure electrode that's closer to how it will be used in a coin cell, for instance. But you still use make an experiment to understand what is happening in one electrode. All right, so it's important to do those kind of experiments using this type of cell to understand how that material works when you have like a few milligrams per square centimeter in the electrode, right? But it's important to remember that energy and power calculation shouldn't be done using a 3 electrode cell. And then you have those two electrode cells. You have the coin cell, and then you also have the 2 electrode Swadlock cell. In this case, you are using only 2 electrodes, and you should balance your cell, like think how much of positive and negative electrode you are using, and then you are closer to the actual battery or electrochemical capacitor as a device, right? In this case, you can calculate energy and power to plot the Raglan graph from galvanostatic experiment, but it's still in a lab scale cell, right? So energy and power will be a little bit overestimated. Half cells in batteries, for instance, when used in just this type of cells, will be closer to a 3-electrode cell than to a device, okay? And then we have pouch cells. And pouch cells have only 2 electrodes, like these 2 previous one. And pouch cell will be the closest in the lab that we can get to the reports that industry asks for. So we are using the minimum electrolyte needed for the cell to work and the maximum active material possible. So let's think on preparing electrodes and cell assembly. So to prepare electrodes, you produce your active material. You have different type of routes to prepare depending on the type of material and the morphology that you want. But then you have a powder that you want to prepare a battery electrode. So this powder will be the active material. But to prepare this electrode, you need to add some more stuff. So you have electronic conductor to help electrons to move in the electrode. You have a polymeric binder, and this polymeric binder will help to hold everything together. And then you have the solvent that will mix everything together, but then you dry out this solvent out, all right? So the proportions may vary, but the idea is to get as much active material possible, okay? So we have different types of binders. Here we have just 4 examples. And the type of binder will tell us how we will prepare the electrode and also which solvent you are going to use. For instance, I have here Dr. bladed clasted electrodes. Doesn't matter the active material here, but for instance, those electrodes could be prepared with PVDF or copolymers of PVDF that normally use NMP or acetone as solvent. You can also use CMC with aqueous-based ink to prepare those kind of electrodes. You can also use PTFE, and PTFE will produce a self-standing electrode. Then you can cut the discs, the electrode in discs, dry them, wait, store in the glove box or use it. So inside the glove box, you can assemble a coin cell or a swage lock cell, as I show you, and then the cell is closed. You can take out of the glove box and use for testing. So other types of cell can be used, like the swage locks I show you, or the pouch cells. But preparing the electrode will be more or less the same. And Dr. blade casting electrode is the most used in the field, right? So I'll talk a little bit on measuring cell potentials. I think this is the question, right? Yeah. Measuring cell potentials and electrode potentials. In this case here, I have a LTO NMC battery. It doesn't matter much on the materials. It's just the cell potential profile, right? So here I'm charging the cell up to a maximum volt potential, holding this potential, and then discharging. So I'm using the battery here, and I'm measuring.
I don't understand. Hey Siri.
I'm measuring the potential during this discharge. So this is a cell potential, right? I'm applying a current for charging and discharging and measure the cell potential of a 2-electrode cell. But what is happening actually is that we have 2 electrodes in the cell that are experiencing 2 different two different reactions, right? So the cell potential is this black line here. And then we have the blue line of the positive electrode and the red line of the negative electrode, right? So this is for battery. So the cell potential here is the difference between the blue line and the red line. In an electrochemical capacitor, you also have the positive and the negative electrode. In this case, they are the same, activates carbon, but they are operating in a different polarization, right? So have the positive and the negative. So this is the cell potential, but actually those are the electrode potential, okay? So the combination of these two electrodes in the electrochemical capacitor or the battery will tell us the voltage, the potential cutoff of the cell during charge and during discharge. For instance, in the battery, we don't want that the NMC electrode goes beyond 4.3 volts. So we want to charge up the NMC electrode. So it's oxidation here. Want to oxidize up to 4.3 volts. And we don't want to go beyond that potential. And that is done by balancing the capacity of each electrode. So in this case here, I have 3.5 more capacity in the negative electrode than in the positive electrode. And it's basically the same here. We need to balance the charge of those two electrodes. The positive electrode can charge up to 1.7 volts, and the negative electrode in the capacitor here can charge down to -2 volts. And the balance of charge of each of these electrodes will tell me where the cell potential will be cut off, all right? And then we think, how do we determine the maximum cell potential, and how you can measure the individual electrodes of this cell, all right? So we have some protocols. Then we use highly symmetrical cell, 3 electrode cells, and do some cyclic voltammetry.
Vitor, if you don't mind me interrupting you, because Thiago lost his connection for there's a couple of questions I think that might be related to now. So one is about the surface area of materials. There's anything more than activated carbon, and the other one is what happens above 4.3 volts, I think, from the previous slide.
Yeah, thank you. So activated carbon is the state of the art for electrochemical capacitors, but you can also have graphene materials, right? But those are in development yet. For the case of going up 4.3 volts, we can start to have degradation of the electrolyte, depending on the electrolyte, or even degradation of the electrode material, okay? So that will depend on the material that we are using. The electrode potential, the maximum electrode potential here depends on the electrode that we are using, and also on the electrolyte. So we need to stay within the safe limits that we are only having the redox reaction that we want to happen, okay? Okay, so now I'm showing how to balance the mass of a supercapacitor, okay? I have only 5 minutes now, and I will show you that we do this thinking on the electrodes of the cell separately. So we have the positive electrode in here and the negative electrode in here. We take the charge of those processes in mind. Then we have the difference of charge of each part of the cell. You can tell when some irreversible reaction is occurring by this difference of charge, okay? And then we have this this relationship that relates the capacitance, the potential of the electrode, and the mass of the electrode. At the end, we have that the relationship of the positive and negative electrode mass will be the relationship of the charge of the negative to the positive electrode. Just an example here, it doesn't matter much the materials, but what we measured. So we used aqueous electrolytes, diluted and highly concentrated with different concentration. We've done those that protocol I mentioned before, and then we can assemble a 2-electrode cell, right? So this is a 3-electrode cell to see how much of potential window we have for each electrode. Then we combine them to have a total potential of the device and the relationship of the mass of both electrodes. Then we have a 2-electrode cell that will be the device. Then we can perform cyclic voltammetry. You see here that the current is constant with voltage, or the capacitance is constant with voltage. And then we also have the galvanostatic charge and discharge. Normally you see those kind of plots in papers, right? So what are those numbers here? So we have different currents for charge and discharge, and then we have capacitance. How can we calculate that? I will skip this part. This is just about the paper, but I want to show you how we calculate those numbers. So here we have the capacitor charge and discharge. To calculate the capacitance, we have this linear regression here. We have the slope of this line. And you have the capacitance will be the current applied, the applied current over the slope of the discharge process. We can get the numbers in here that from this calculation, and then we have 23.4 amps over the slope of this potential over time times the mass of the electrode, because I use it here 0.1. That was the current used for charge and discharge. All right. So this is the capacitance for this cycle here. And then we do this for all the cycles we perform. You can do some coding to automate that kind of calculation. And what about energy and power to plot the Ragon plot? So I have the same galvanostatic experiment. So we apply the current, is the same one, and measure the voltage. We have that energy is current times the integration of voltage over time. Then we have, it's the same current. This is the integration of this, only the discharge curve. So it's the area under this line here of the discharge. So we have the value in here. All right. So this is voltage per second. Remember that energy, we want watt-hour, and then we have that 1 hour is 3,600 seconds. And we also want per kilogram. So I have that 1,000 gram per kilogram here. And that's how we calculate the energy of this discharge, all right? And how do you calculate power? From this integration here, we also have the discharge time. So the discharge time is the difference between just those two times. So the time that the discharge started down to the time that the discharge stopped. So this discharge lasted 500 seconds. So the average potential, the average power will be the energy over this discharge time, okay? So we have the energy, the discharge time, and then we have the power here. So that's why I told you in the start of this class that normally we report average time. And then if you want to know the instant power, the power is changing over the discharge. So the instant power will be current times the actual potential at that time. So this one here is the average power. And I just show you how I calculated this point in this graph, okay? So we have 14 watt-hour per kilogram and almost 100 watts per kilogram.
Sorry, Vitor, to interrupt you.
Yeah.
We have two questions here.
Okay.
And first one is Andre's is talking about the curve in slide 16. Were obtained performing different experiments for each electrode to obtain each electrode potential.
No, so here, well, actually, can I answer this question using my next slide?
Yes.
So
after you answer, we have another one, and
okay.
I will mention after.
So this graph here is similar to that one, but it's for a capacitor. So gray line is cell potential, red line is positive electrode potential, and blue line is negative electrode potential. How do we measure that? There are different equipments that we can measure in different ways, right? Depends on the potential stat that you have. Normally in battery cyclers, you have one channel to perform the galvanostat experiment. So you are connecting a 3 electrode cells, but the main channel will be connected to the positive and the negative electrode only. You see that this channel here is not connected to the reference electrode. So you are applying the current and measuring the potential. And then you have 2 auxiliary channels. So the first channel will be connected to the positive electrode and to the reference electrode. And the second one will be connected to the negative electrode and the reference electrode. So in this channel here, you are measuring the potential of the positive electrode. And in this channel here, you are measuring the potential of the negative electrode, all right? And then you have one cell that has 3 electrodes, but it's actually operating as a 2 electrode cell. And the third electrode, the reference electrode, is only used for sensing the potential of the individual electrodes, all right? I hope that answered the first question.
Thanks.
André, say thank you. Oh, thank you, André. And there is another one from Katerina. Katerina is, in order to study the stability and lifetime of the capacitor, how many charge and discharge cycles is in the recommended to obtain?
Yeah, that depends a lot if you are using pseudo-capacitance or only double capacitance material. Normally, from 10,000 to like 100,000 cycles in a capacitor. We have been reporting like within this range, you know. For pseudo-capacitance, people tend to report less cycle, like 2,000, 5,000 cycles, all right? And that the current that we are applying is important. So if you apply a current that's too high, then you only have practically resistance, and then the capacitor will last longer than if you apply a smaller current. There are different types also of protocols to evaluate how long the capacitor will last. You can hold the voltage. There are a few papers on that, all right? So cycling is not just the only way to measure this type of experiment. So I had a better example here, but I think I will skip so I don't take time of the other people. But just to say that you can use different, the same kind of cells, same types of electrochemical procedures to calculate fundamental parts of the development of battery materials, all right? So in here, for instance, you can calculate how the redox reaction is taking place in the book or the surface of the electrode when that matters. Then we have also galvanostat charge and discharge, plot specific capacity. Remember that capacity is just time times current. You can also take this curve here from a galvanostatic experiment that you are measuring potential. You have the derivative of capacity in function of potential, and that resembles a lot the cyclic voltammogram that you done before, right? So this is a nice way to look to your data. So I would like to thank you for the attention, everyone. and also Thiago for this opportunity. I just would like to say that they have open positions in our group here in São Paulo to work with capacitors, batteries, and especially metal batteries. If you are interested, please just write to me and we can talk about it. If you have more questions, I'm open.
Thank you very much, Vitor, for the very nice talk. And storage is a good topic, and the participants made a lot of questions during the presentation. Anyone have more questions? The people is only giving you thank you for the very nice lecture, and everybody give you thank you. I will thank you too, Vitor. Thank you very much to help us with the first day, and thank you very much to share your experience with the energy. I hope that we can discuss more about this in the future and try to put together sensors and energy storage together. Thank you very much.
Thank you for the opportunity. Thank you.
Our next speaker is André. I would like to present André first. André is the first time that he's coming this week, and André de Oliveira is currently working in the electrochemistry and spectroscopy field at Metrohm, Brazil, performing installation, supporting, training, and lecture activities in courses and seminars through Brazil and Latin America. André has the bachelor degree in chemistry from the University of São Paulo. He did an internship at the University of Florida with a PTASchool during the undergraduate, master in chemistry from the same university from 2010 and 2012. Additionally, André, in 2018, started a personal scientific dissemination project. It's a very good channel in the YouTube. Sorry, but it's in Portuguese, but it's a very good channel. And the literal translation, the science that comes with history. He has a semi-finalist at the FAMLab Brazil and become a national scientific communicator leader member. André, thank you very much to come here. André is working with Metrohm and give us a lot of support with our equipment. And thank you to accept the invitation to be here to talk now with us about energy again and try to complement the Vitor's talk. And thank you very much again. André, the stage is yours now. If you like to try to share your screen, it's with you now.
Okay. Thanks, Thiago, and thanks, everyone. Thanks for the presentation. I'm very glad to be here with a lot of people that I know from a long time ago in this electrochemistry area that I like very much. And I think it will be a very interesting discussion because it's very complementary to what Vitor said right now. So can you see my screen? Is everything all right?
Not in the full screen yet. Try to unshare and share the full screen, not the window.
Okay.
Check if it works.
I asked you previously and I did it wrong.
No problem. It happens with the Zoom sometimes.
Let's go. Screen. Okay, now I think it will be all right.
Perfect. Oh. It's with you. Thank you again. Yes.
Okay. Perfect. So hello, everyone. As Thiago said, my name is André, and I'll be talking about solutions for the development and characterization of energy conversion storage devices. So at first, for those who doesn't know Metrohm, Metrohm was founded in 1943 in Herisau, Switzerland. It's a city in the east part, it's east of Zurich. And until now, we have the headquarters at Metrohm. But now Metrohm is a global-wide company. It has distributors all over the world. So right now it's 41 subsidiaries and 44 independent distributors. And here in Brazil, Metrohm Brazil is actually the center for support in the whole Latin America. So Central America and South America, we give the support here for our distributors. We give presentations. So we give the support for the whole Latin America in all Metrohm lines. So here I'll be talking about electrochemistry. That is one of the lines we have very dedicated to research, but we also have equipments in titration, ion chromatography, spectroscopy, online equipments that can measure like inside a reactor or inside a line of production. For those who want to know better Metrohm, I invite you to go to our website where you can find a lot of more information. So the discussion today is about energy, and the energy sector has a constant demand for new solutions. So here in Vitor presentations, we could see some discussion about different ways of generating energy, and we can think about a lot about vehicles that we use in our daily routine, and we still have a lot of dependence on fossil fuels. So a first discussion would go environmentally speaking, but there is also economically speaking. We constantly have like oil crisis since from the 70s, and right now we're having an oil crisis here in Brazil. The prices went high up, and this is impacting in Brazil's population. But if we think about power grid, there is also a demand for solution, because as Victor already said, here in Brazil, we have a lot of power from our power grid coming from hydroelectric energy, and it's not a constant source of energy. We depend a lot on our rain seasons. So when the rain season is not very good, we have shortness of energy, electrical energy, and this impacts in the population lives. So storing this energy would be very interesting, so we can use as we need it. And inside this debate, what may electrochemistry offer? What can the science of electrochemistry offer as a solution for generating energy and for storing energy? And let's think about a world where we have like electrical vehicles, and we have like fuel cells, solar cells as our main source of energy. We can think about a world where electrochemistry can act in a lot of places, because every car will be using a fuel cell or a battery, and we have battery uses also in power grids in households. So we may think about the future if all these technologies actually if they go right, if in the end we have like all the products coming from energy from our electrochemical devices, there will be a lot of places in the market for those who have knowledge in electrochemistry. So here we have a lot of students, we have like professors, PhDs and master students like me, and it may be a very bright future for electrochemists where we have a lot of positions. So those are some of the reflections I want to bring today for my presentation. And I don't know, I think there's a lot of young people here, but you may remember some of them, the Hercules movie, the cartoon from Disney, where we had the gods. And I think it was very nice because Zeus, who throw the lightning bolts, Zeus did not produce the lightning bolts. He had like a bunch of bolts in his hand. And there is even a scene where baby Hercules plays with the bolts. And Zeus has in the clouds, the bolts are all stored. And who produces the bolts is another god. And I think in English, the pronunciation is Hephaestus, but I'm not sure if this is right. But it's the god from the left, it's the god of the inventors and the blacksmith and everything else. So I'm doing a parallel here because we may think about generation and storage of energy. And we'll be talking about this today. So we need to generate the electrical energy, and is what we do with some devices. But there are other devices, is what about Victor was talking right now. They have the main purpose of storing this energy so we can use it when it's needed. So this would be like, in a way, what electrochemistry can offer in a general way. And about the second topic, where electrochemists can act. So if we think, as an example, in the production of an electrical vehicle, so it all starts with fundamental research. We may think about understanding physical and chemical principles, development of scientific models that maybe we don't even know with the applications, where is it going to go? And then it goes to exploratory research, where there is the development and characterization of materials, and we try to improve performance. So it's not only ideas and principles, we are actually producing the materials. And then we try to apply those materials. We try to validate the concept, we try to show some for performance and a little bit of optimization. And then, but this is doing at first in our lab, in our, you just build not even a prototype, something just to prove the concept. And then you go to prototypes, that is development and demonstration, that is getting more and more connected to the industry. So we have startups, we have like companies incubated in universities that are trying to get those technologies to real life and show that these may be the future. These may be become a product and then can go to people. And if everything goes right, we'll have this M4. And I'm sorry, M stands for maturity. So those are maturity levels of the research and development. And in M4, everything went right. There will be a large scale production. In a large scale production, we have to think about all the process, the component manufacturing. There's the production of anode, cathodes, electrolyte, separators, cell manufacturing, model production, battery pack assembly, where you have to always make the performance tests and quality control in all of those steps. So you get a final product that has the integration of all this technology that came from basic science at first. So if you think, all those maturity levels are places where electrochemists connect. So it's very interesting to think in a future that everything that we study, and it's been a long time, we have a lot of different electrochemistry groups here in Brazil. So all this knowledge, it may be very applicable in our future, and having real positions in the market and acting in different ways. So in this presentation, I'll be talking about some solutions to help those paths with solutions from the Metrohm group and the Metrohm partners. And it will be mainly focused in the three first maturity levels, M0, M1, and M2. But it's not like we may expand and go to other different maturity levels, but at first we'll be talking about M0, M1, M2. What can we offer for researchers and developers to improve this scenario? So at first we're talking about generation. So let's pray to Ephistis to have a good presentation here. And we'll be talking about fuel cells and photovoltaic cells. So here we have two examples, a proton exchange membrane that I'll be talking right now. And the second one is a perovskite cell. I don't know if the pronunciation is right. I hope it is. Just let me get the pointer. Okay. So the fuel cell. A fuel cell is a device that converts the energy, the chemical potential energy, that is the energy stored in the molecular bonds, into electro energy. So we have here in the left a proton exchange membrane. This is not the only type of fuel cell. This fuel cell works with hydrogen, but we also may have fuel cells working with ethanol, methanol, that are biofuels and different kinds of fuels. But when we talk about the fuel as the hydrogen, we will have a catalyst at the anode that has the function of separating the hydrogen atoms, breaking the bond into hydrogen molecules and generating protons and electrons. So this is why we call the proton exchange membrane. The electrons, they will go through the circuit so we can use their energy, while the protons will flow through the cell. They will flow through a separator that is a membrane that allows the passage of ions, but not electrons. Because if electrons went this way, we would have a short circuit. The protons migrate through the electrolyte and they get to the cathode. In the cathode, we'll have oxygen coming here, and the protons will encounter the oxygen atoms and also the electrons that are flowing through the circuit. So this will close the circuit, and we will be producing water as water vapor generally, and also heat and electricity. Well, if we think in a fuel cell, it has very similarities with batteries. We have two electrodes, we have a separator, and I would say that if we compare it, in the battery, we have a closed system. So all the reactants, all the products are inside the battery. In a fuel cell, this is different. We need to get the fuel coming in, the oxidant, in our case, it's oxygen, and we are releasing products. And we may even say that hydrogen is actually, we don't have like big natural sources of hydrogen. We need to produce it, and mainly for electrolysis. So we may say that hydrogen is just an energetical coin. We convert it to use as we need it. So we are just storing energy in hydrogen bonds. So some researchers are also focusing in the part of producing hydrogen. So with photoelectrocatalysis mainly, so we can use energy, solar energy to produce hydrogen, and then hydrogen can be used in fuel cells. Okay, so in the next, the main challenge we have right now with those fuel cells are basically they're expensive because they use a lot of materials that are expensive, like platinum or metals from the platinum group. Here in the right, there is a graphic showing it's actually not the proton exchange membrane, it's an alkaline fuel cell, but you can see that a lot of materials come from platinum or the full cell, or at least the cathode or the anode. So very few works with platinum-free cells. And we also have a concern about the storing of hydrogen that is a very highly flammable gas. So there is the safety issue, but here in the presentation, we'll be focusing in the part of the the materials we use in the fuel cell. So talking about fuel cell, we need to talk about electrocatalysis. This is very important. When, as I said, the catalyst in the anode is where everything starts. So what is electrocatalysis? Electrocatalysis would be the study of electrochemical reactions with the goal of increasing the rate and efficiency, while the electrocatalyst is the part, it's the element that accelerates the rate of an electrochemical reaction, and or it may decrease the overpotential required for a reaction to occur. So if we look at this plot here in the bottom, you can see that the red line shows a poor electrocatalyst. Why? Because we can see it has a high overpotential for the reaction to start, and after the reaction started, the current doesn't increase very much while I increase the overpotential. While the green plot, we can see that the overpotential is very low and the current increases a lot with just a few increments of the overpotential. So this is what we look for a good electrocatalyst. And I like to say, especially when we have students, the overpotential, when we talk about overpotential in your daily routine, when you assemble an electrochemical cell, and generally the potential stats have some display, or you can in the software show the display and see the potential of the cell before starting the experiment. This is the potential of equilibrium of your cell, or we can call it the open circuit potential. So the overpotential would be when the equipment, the potential stat, will force a potential higher or lower than this potential of your cell. So if the potential stat is showing 0.3 and you apply 0.4, you are applying positive 0.1 over potential. So here, be careful, because we're talking about over potential. It's not the potential that you directly see. I think you discussed this a lot during this school. Unfortunately, I could not participate from other days, but I'm pretty sure you'll be covered in this topic. So the electrocatalysis research has different focuses. We may focus on design of electrode materials that look for new materials or improvement of surface properties, electronic properties. This may be a focus to improve and get these results we need. But we also may talk about optimization of the reaction conditions. We may talk about electrolyte composition, the presence of reactive species and intermediates, how to find the best pathways inside an electrochemical reaction. And we may also improve it about temperature and pressure for your work conditions. Cyclic voltammetry is the first technique that I'll be talking here today. We can see here in the right is a cyclic voltammogram of platinum in sulfuric acid. This is a classic for electrocatalysis. So if you will start in electrocatalysis, or if you want to study a little bit more, start with this. This is like the gold standard for electrocatalysis. We can see the formation of platinum oxide, the reduction of platinum oxide. So those are surface phenomena. We can get the double layer capacitance here by the difference in the forward and backward scan in the cyclic voltammetry. And here is our main focus for the proton exchange membrane is the hydrogen desorption and adsorption region, where we can see the hydrogen being generated or consumed. So cyclic voltammetry is very important for different fields in electrochemistry. Here in electrocatalysis, We may use it to determine the stability window of the electrolyte, to investigate the general redox behavior, to determine the electrode surface area for quantitative comparisons. I'm pretty sure you had some discussion about electrode surface and how we can calculate it, the difference between geometric area and active area. There are different approaches, so you can get an accurate result. We may use cyclic voltammetry to investigate the stability of electrocatalysis. I can make many cycles as I want. Investigate the reversibility, determine the apparent activation energy of the reaction. This we do when we vary the temperature of the experiment. And those three last topics are when we combine cyclic voltammetry with different techniques. So we may combine electrochemistry with spectroscopy to get spectral electrochemistry, and we may determine the molecular structure of products or intermediates. We may use electrochemical quartz crystal microbalance to investigate material deposited or removed from the electrode surface. We may use the rotating ring disc electrode to investigate products and short-lived intermediates via their electrochemical response. So look at how many things we can do with cyclic voltammetry, which is a very basic technique. But there is another important discussion. This hydrogen region here, we can see that this may vary considering the technique and the equipment that you'll be using. So the hydrogen adsorption and desorption occurs in a time scale comparable to the buildup of the double layer. So if you use a digital scan that in the software generally we see as the CV staircase. So the staircase is because we're making a digital scan. So we will be losing information because we were only collecting the current at the end of the potential step. And the information about the current at the beginning of the potential step will be lost. And look how the voltammogram looks like. If we use the CV staircase, this is the black line. If we use another kind of system that is a system with an integrator, so I can calculate the charge and then derivating this charge, I may get a current. I will see this blue line, which has a little bit more of the signal, but the red line is the best. The red line uses an analog scan. So an analog scan can be inserted in some equipments, and this will give us the best scan we may have to perform in electrocatalysis. So we have different equipments in Autolab, in Metrohm Autolab, and the first question you should be asking yourself is, which potential stat should you use? So Vionic, powered by Intel, it was launched this year, and it's very that may install. Here I have a message here saying that my internet connection is unstable. So if we're having problems, I'll just check the cell phone here to see if there is any kind of problem.
It's okay now, André.
It's okay?
I think you could talk about Vionic again. Please.
Yes, yes.
Oh, okay. So Vionic was launched this year, and it's a outstanding equipment. I'll be talking about him. And Vionic, it has included in the hardware the analog scan. So if you have a Vionic, you can perform analog scan with no problem. The modular line, which has the 302 or the 128, we may insert a scan 250 module so you can perform analog scans. And if you have a compact Autolab, the 204 and the 101, you have a built-in integrator, so you can perform the blue curve I showed here. Is this one? It's performed. We call it the integrated current. Is the name we have to this kind of experiment. So those are the different equipment. So be careful when we choose the technique and the equipment that you will be using. Sorry, sometimes my English is a little rusty with all this pandemic. And talking about Vionic, we have a huge voltage compliance. We have 50 volts of compliance. We have maximum currents of 6 amps that are very good for different kinds of application, including batteries and fuel cells. Vionic, it has a built-in electrochemical impedance spectroscopy with maximum frequency of 10 megahertz. So it's very good. It's top of the line. and it has a faster processing for electrochemical impedance spectroscopy measurements. It has a dynamic interface. If you look at the equipment, it's always giving signals, light signals with color coded, showing what the equipment is doing and what it can do if there is a problem or not. Selectable floating is interesting if we talk about systems that are grounded. It has a built-in analog scan, as I said, and some features I will be mentioning later that are the second sense. It's networked and it has a very big internal memory. This will be very good for the battery experiment. So I'll be talking about later in this presentation. Oops. So from our modular line, we also have like very interesting features for catalysis, because we have the analog scan, the impedance model, but we also have some models that at this point, they are not currently available for bionic. So if you want to work with bipotential stat, rotating ring disc electrode, electrochemical quartz microbalance, measurements of pH and temperature while parallel to the electrochemical experiment and spectroelectrochemistry, our best solutions will be with our modular line. And now I'll be talking about one of those features, that is the rotating ring disc electrode, that is very interesting for electrocatalysis. So a rotating disc electrode is an electrode that we may control the mass transport that is occurring in the electrode surface, electrode interface. When we have a steel electrode or steel solution, the reaction will be limited by the diffusion of reactants to the electrode surface. So you don't reach a steady state, because when we get to the potential peak, if we see this voltammogram, this blue line, we can see that a drop of current. This drop of current occurs because the diffusion layer, it increases with time while you are scanning. So we don't have a stable, a steady state here. If you compare this to a rotating disc electrode, which is the red line, you will see that when you get to the maximum, to the peak of potential, the current stays on top, because we don't have this expansion of the diffusion layer. And we can even control the diffusion layer by controlling the speed of the rotation. So electrode rotation allows a reproducible steady state flux to be established and maintained. And if we talk about a we can get like information like the Levitch plot and the Kutek-Levitch plot, but I'll not be talking in this presentation, where you can get the number of electrons, you can get the constant rate of the reaction. But in this presentation, I'll focus a little more in the rotating ring disc electrode. A rotating ring disc electrode, it is rotating as the previous one, but if we look at the electrode, it has a disc in the middle and a ring around it. And there is a layer, this gray layer here, it's not conductive, it's a polymer generally. It may be a glass, but generally is a polymer. So you have the second electrode that allows a second reaction to be studied. And it's very interesting because the ring is subjected to the same conditions, the same electrolyte, the same rotation, the same temperature, and it has some unique features. I may use a different material, I may apply a different potential, and with this, I can study the products and the intermediates formed at the disc in the ring. So the signal of the ring, it may be an indicative of the reaction pathway. And this may be used to study the oxygen reduction reaction that occurs in the cathode of the fuel cell. So the oxygen reduction reaction, we're talking about the dissolved oxygen that is in the solution. It may go through different pathways. So there is one of them is the 4 electron, that is the most efficient and desirable, where we go from oxygen directly to water. But we have a different path of the reaction that can form hydrogen peroxide as an intermediate. So how can I study if my electrode, the system, if I modify the surface of my electrode, is it improving this reaction or not? So let's study if it's going for one way, the second way, or we may have mixed behavior, and we can see if it's mainly in the 4 electron or mainly in the 2 electron. So the electrode is rotating, all the products generating are being thrown to the borders of the electrode, and they will pass in the surface of the ring. So if the ring is polarized in a potential that may reduce the hydrogen, it may oxidate the hydrogen peroxide to hydrogen, we will detect it in the ring. And we may say that if I have a signal in the ring, my reaction is going to the 2-electron way. If I don't have reaction in the ring, my reaction is going to the 4-electron pathway. And I can see this in a voltammogram. Actually, are 2 voltammograms. One is the disk, one is the other one is the ring. And we can see that when the reaction starts in the disk, if there is something being detected at the ring. So this is the main purpose. We can investigate it. So it's very important for fuel cells. We can characterize this oxygen reduction reaction. And for fuel cells, I also recommend you to go to our website. We have a tab called Applications. In the Application tab, if you look for EC014, you will find this application note with much more information, so you can learn about the oxygen reduction reaction. I will not be able to explain everything here in this presentation, so I invite you to go to our website, download it for free, and it has a brief explanation of this kind of experiment.
André, sorry to interrupt you.
Okay.
We have a question here. I think that you already mentioned, but Marian is talking about, would like to please explain more the advantage of the rotating disk in comparison to a normal electrode like glass carbon. I think that's the idea. The main idea is to study electrochemical reactions, mechanisms, but if you could please send more than that.
No problem. Well, is what Thiago said, it depends on what you want to do. So if you're just investigating a general behavior of a material or an electrode, you may study.
Let's wait and return. But Marian, normally these electrodes. Oh, what are? I will try to answer until André will return. But the idea here is that the material of the electrodes, like the ring disk electrodes, could be different materials, like gold, platinum, depend of the material that you are using and the reaction that we are trying to understand or study. This is the idea. But the common materials normally, they are platinum, gold, glass carbon, and these are the 3 main materials that we have. About the other question that André mentioned, André is back again.
Okay, here.
I was talking about one of the other questions that about the materials used in the rotating disk. Normally are gold, platinum, and
yes,
glassy carbon.
We also have glass carbon.
Yeah, and until your internet is unstable, you are talking about the rotating disk and the study. You are starting to answer the question, and your internet fell.
No problem. So with the rotating disk, I can have information about diffusion coefficient of species. This information I can get from the Levitch plot. And it may be an easy way also of finding, if you have already the diffusion coefficient of a species, if you act with the redox mediator, you may find the number of the electrons in the reaction. So you can use for this purpose. And with the Kutek-Levitch, you can also find information about the kinetics of the reaction. You can get the constant rate of this reaction. And so I would say it's for different purpose. If we talk about sensors, we may have a higher current if you're working with a rotating electrode, because you're making it easier to get species to the electrode surface, and this will increase the signal, but you have to look, this will not increase the noise too. So I would say that using a rotating electrode, it depends a lot on what do you want to do and what do you want to study. But you can get improvement of some signals. And as I said, even with sensors, I can get different approaches if I work with a rotating disk electrode. So I hope this answered the question. And is there another one, Thiago?
No more. Only Marian that made the question for you is saying thank you.
Okay. So just to finish here in fuel cells, if we talk about cells to use in your laboratory, we have different solutions in Metrohm and our partners. So we have at first here, it's a cell to work with a rotating ring disk electrode from Autolab. And this is ideal for an Autolab system. It already includes reference electrode, counter electrode. There's purge valve for working with inert gas, inert atmosphere, Teflon lid. And then we go to cells from Redox.me, that is one of our partners. And Redox.me has a lot of interesting cells. I really recommend you to go to their website and take a look. This one is a hook clamped assembled photoelectrochemical cell. So this hook clamp here, it makes very easy to open and close the cell. We have a window here so we can irradiate some illumination and work with photoelectrochemical experiments. And it also has those gas inlet and outlet, so I can collect the gases or I can purge some gases here if I want to remove the oxygen in some ways. Here is an NMR cell, so I can make electrochemistry with NMR in situ. So this is very interesting. I will not be talking a lot about it, that it has some configurations you can find in our website, but here is just a closer look. Here is the cell as disassembled. Here is a closer look. And the last one here is, again, a photoelectrochemical cell, but the difference is this one is an H cell. In an H cell, we have the anode and the cathode separated by a membrane here in the middle. So this is interesting because I can separate the products generated in the anode and the cathode. So it's very important for electrocatalysis studies. And we may also work with flow conditions. So we have these tubes here in this side and the other side of the cell. So I can work in flow conditions, both sides of the cells. I can work with irradiating some light, so photoelectrochemistry. It's very interesting, those cells. So I'll be talking about photovoltaic cells. So the photovoltaic effect, it's commonly observed in semiconductor materials. And it's common in semiconductor materials because if we compare the distance between the valence band and the conduction band, we can see that the distance is very short comparing to isolating materials and comparing to metals where we have in metals, we have the overlapping of those two regions, but in semiconductors, the electrons can be promoted by absorbing light or even thermal energy, but at a low price. And characterizing those photovoltaic devices can give us parameters related to the performance of the device and the structure of the materials. So the electrochemical techniques I'll present here, they can be used with a potential stat, galvanostat, Autolab, using the Autolab LED driver kit, which is this one here. And using an impedance model, you will expand the possible measurements. So just do not confuse it because this is not spectral electrochemistry. We are not getting spectrums here. We are just making photochemistry. We are photoelectrochemistry. We will irradiate the device with some energy and we will characterize the device, the response when we're stimulating it with different wavelengths. So this is an LED. We have to change the LEDs when we change the wavelength. So those are the techniques that we can explore with this kind of system. This little circle here, it only represents if it's green, the signal is not modulated. If it's orange, the signal is modulated. The upper part of the circle refers to the light source, and the lower part of the circle refers to the potential stat galvanostat. So the first two techniques doesn't need modulation. Electrochemical impedance spectroscopy only needs the potential stat modulation, and the techniques IMVS and IMPS, they modulate both the light source and we need a modulated signal to be analyzed by the potential stat galvanostat. So at first, the IV curves are these are the most basic technique to characterize a photovoltaic device. In this kind of technique, we will irradiate the device with some light, and we will scan the potential while we measure the current. We're actually draining the current because this is a device that generates electricity. So from this plot, I can get the open circuit potential, is the potential where the current is near zero. I can get the short circuit current, is the current where the potential is zero. I can get the maximum power point of this cell. I can get the fill factor, efficiency, and the quantum efficiency that we also call the incident photon to current efficiency. So the thing is, efficiency, I would only have to know the power from the light source and the power generated by my cell, the maximum power point. That would be the efficiency. But this is not considering the different energy of the different wavelengths. So to get the energy from the wavelength and get the efficiency I'm getting for this wavelength I used in my experiment, I need to calculate the incident photon to current efficiency. All those measurements can be done automatically with the Nova software, both the measurement and the calculation. So we have procedures that are already assembled, and you get all those curves with all the data treatment. So you, in just one click, you have all the information in your hand. So it's very easy to use because you don't have to get the data, go to another software, and then treat all the data you're collecting. Again, I invite you to go to our website in Applications tab. If you look for the PV application notes, are the photovoltaic application notes, and the first one is about dye-sensitized solar cells, and they show the IV curves. Charge extraction is an experiment focused in dye-sensitized solar cells. So here is the general scheme of a dye-sensitized solar cell, where you have a dye that absorbs photons, and the electron will be promoted from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. Then this electron can be injected in the conduction band of a semiconductor, so we can get the energy from this electron in our device. To complete the whole scheme, we need a redox mediator that will be getting the electron in the cathode here. Generally, it has platinum on it, and it will regenerate the dye so the cycle can start all over again. So the charge extraction technique, it's a series of you keep turning the light on and off while you're measuring the potential and current during OCP and short circuit conditions. So Nova uses a combination of chronoamperometry and chronopotentiometry, and we can get information from the back reaction. The back reaction is something we don't like. It's what happens when the electron, instead of going to our circuit, it goes back and regenerates the dye. So it excited in the dye, injected in the semiconductor, but from the semiconductor, it goes directly to the dye again. So this is the back reaction. This is not good. And for a solar cell to have an operation, a normal operation, this must be very slow. So we can get electrons accumulated in the conduction band of the semiconductor, and we can use this energy to power a device. There is the application note. It's the PV04. Again, I invite you to go to our website. And we may use electrochemical impedance spectroscopy. It may be used in different fields. It may be used in fuel cells, in solar cells, and in batteries. It's a very good technique to allow to study the electrode solution interface phenomena. And as a general definition, the different electrode processes vary with the frequency because they have different speeds. So when we are in very high frequency, we can get information about the solution resistance in a general way. If we go to lower frequencies, we'll be starting to see some double layer capacitance behavior, and then this behavior starts to mixes with the charge transfer reaction. And we have here in the same circle influence of both the double layer capacitance and the charge transfer reaction. And then in lower frequencies, we may have lower processes, that is slower processes, like the mass transport. So like diffusion, we have this in lower frequencies. So we can characterize a lot of devices and show how those different processes that are commonly observed in electrochemical systems and how they perform. For this, we generally use some models to get some quantitative information from the data. And Nova software has the equivalent circuit analogs built in the software, but there are different approaches that you can use if you treat the data somewhere else. Again, application note, only for this kind of measurement, impedance with dye-sensitized solar cells. Here is a general behavior of a dye-sensitized solar cell. And the last technique we'll be seeing in photovoltaic devices is the MVS and IMVS and IMPS. They give us information about the electron lifetime and the dynamic of electron hole recombinations. So the IMVS, it will give electron recombination information, and the IMPS, the electron transport information. So the steps are the same from electrochemical impedance spectroscopy measurement, but we are applying the amplitude signal, not to the electrochemical cell. We're applying to the light source. So the light source will vary in its intensity in a determined frequency, and I will make a frequency scan. In the different frequencies, I will be measuring either the potential or the current from the photovoltaic device. If I have the relation between the light intensity and the voltage of your device, I have IMVS. If I have the relation between the light intensity and the current of the device, I have IMPS. So I'll get some spectrums, just like in electrochemical impedance spectroscopy, and I can characterize my device showing if it has higher recombination or higher diffusion of the electrons inside the cell. And well, to finish my presentation, I'll be talking about batteries, but a lot of things that I'll be saying here, Vitor already said, so I think it's very good from the part of the characterization of the devices and the main parameters. So I will speed up in some parts because I think Vitor already mentioned. So here is the definition of a battery or two electrode system with a separator soaked in an electrolyte that allows ion movement. And I think all of this already was mentioned in Vitor presentation, so I'll be not mentioning everything again. So we have the main composition of the electrodes, graphite, I think it was very nice, Vitor presenting the Nobel Prizes and how these evolved. Here again is just the mechanism of the lithium-ion battery, and we can see the charge and discharge. Vitor already explained how it works, is the intercalation process. And here is a part of the characterization of the batteries. It's this feature, I'm not sure if Vitor mentioned or not, so I'll be mentioning here. So the C rate is a value that we call, it's the current that you would have to apply to charge or discharge your battery in 1 hour. So this battery you may buy in the internet is a Samsung battery. It has a nominal capacity of 2,600 milliamp hour. This means that to fully charge or discharge in 1 hour, you would have to apply 2.6 negative or positive amps. And there is an important thing here. If you use higher C rates, if you charge or discharge with a higher current, it will charge or discharge faster, but you will be losing capacity. Or in another word, there will be less charge in your battery for you to use if you try to speed up the process. So the Ragon plot, Vitor already explained. I think it's very interesting. And there is this analogy that I like. Every analogy has a problem, but if you think here, it's comparing the specific power and the specific energy. So if you think in a device that has a high specific energy, it can store a lot of charge, but sometimes it cannot deliver all this power. So we think it is in this bottle, even if the bottle was huge, but the head of the bottle was a very small hole, we wouldn't have a lot of power. But if you have a bigger hole in the bottle, you have a lot of power, but your energy stored will be run out very quickly. And I think it's a nice analogy to compare specific energy and specific power. But the Ragon plot was discussed a lot by Vitor. This is another plot that Vitor described, and I asked Vitor that question because I wanted to use in my presentation. So Vitor discussed a lot about the cell voltage, and we may have this voltage because we have the voltage from each electrode. I asked him how he was getting those plots, if he was making different experiments, and you could see from his answer that he was using auxiliary channels. He had a cell, the whole cell was being measured by the potential stat galvanostat, but he had auxiliary channels to measure the potential from the working from the anode and the cathode. But this is one of the interesting features of Bionic. Bionic has a second sense. The second sense is a feature of Bionic that allows the measurement of a second electrode against the same reference electrode. So it's a true parallel path. So the signal is not multiplexed. The signal acquisition has a dedicated path for it. It's available in floating modes, and it allows us to get the counter electrode versus reference potential during a cyclic voltammetry, a charge discharge, or even you can get spectrums from the counter electrode in an spectroscopy impedance measurement. So for those who already know Autolab, you'll be seeing that there is a second connector black, a second black connector, the S2. Because of this S2, we can get the potential against the reference electrode and the counter electrode, while we have the potential of the working electrode and the reference electrode. So I have sense 1 and sense 2. So here in the cyclic voltammetry, we see the potential of the working electrode, and in orange, getting darker, is the potential of the counter electrode. So this is very interesting for batteries because I can have the plot that Vitor showed without an auxiliary measurement. The equipment will be measuring from one side and the other side of the Swadlock cell type, and we may get the cell voltage by making the difference between those two potentials. I can even get impedance plots of the counter electrode.
Can I ask something on that?
Yeah. Yes.
So in this configuration, the potential that they are measuring the working electrode is versus the reference or versus the counter electrode?
The reference. So
it's a little bit different than using auxiliary channel, actually. So you see?
But if I got the auxiliary channel was measuring between the working electrode and the reference electrode, or no, I was mistaken.
The auxiliary channel was measuring between counter and reference and working and reference, but the main channel was measuring against working and counter. You see? Okay. So it's a little bit different, but it's great. Yeah, you can measure, you can follow the counter electrode voltage potential, right? So
yes, but just for me to be sure, if you get those two auxiliaries and you make one minus the other, you would have the cell voltage. That is what the main channel is measuring, right?
Yes.
Okay, so I think this would be the idea here. It's like the two potentials we're getting is like the two auxiliaries. And if we want to get the cell voltage, you would only have to make one minus the other.
Yes, of course. Yes.
So that's the idea of the second sense. So it's very good for batteries. And we also have different features. So it answers, Vitor, your question? Sorry.
Yeah, yes. Thank you.
Okay. So we also have computer-free measurements. This is very nice because some battery experiments may be very long, some cycling experiments. So you can untether your computer, you unplug it from the equipment, and the software will tell you how long you can stay disconnected. And when you plug it back, you have all the data. The equipment always show by light signals if the experiment is running or if it has ended, and it can store 10 million data points inside the built-in memory. The seamless is very nice too because there is no time gap between the commands measurements. So when we change from one cycle to another or one technique to another, you can see by this example, I'm applying cyclic voltammetry, linear voltammetry, and steps of potential. And you can see that when I get from a linear sweep voltammetry to a step of potential, the interval time between the points does not change. We have the same interval time. So this is the seamless transition. I will not be losing any information. So it's very good for charge-discharge. Vitor already talked about a lot from what we can get from a charge-discharge cycling experiment. So here is just an example using software Nova. And here are some parameters we get from charge-discharge cycling: the state of charge, the depth of discharge, the state of health. We can see when we compare the charge we are accumulating in the battery comparing to the initial one, because with time, everyone has a cell phone that with the time it has less and less charge on it. And those other parameters I think Vitor already mentioned, so I'll be hurrying a little bit so I don't get time from Gabriel. Impedance is very important to batteries too, because batteries should have a very low impedance, but with time, with charging and discharging, we have some parasitic reactions that will increase in the impedance of the battery. And we get this scenario here with a used battery. And this is bad, so we can have impedance between some cycling, charge-discharge cycling, so we can monitor the condition of our battery and how is it working. And I would just like to show you those other application notes. Go to our website, download it, because it's important information about connections. So the best way to work with batteries and energy devices in a general way is what they call the Kelvin probe. So you should separate in an AutoLab system the sense and the reference and put them as close as you can to the device. And the counter and the working electrode, you can plug it here. So you can see that there is some shift in the impedance spectrums if you change the way you connect the device. So there's no time for me here to explain a lot. So EC018, EC013, we'll be talking about those connections. You can find the information in our website. Oh. Well, this technique, I will not have time to discuss it, but it's a technique to use to measure the diffusion coefficients of electrons inside your battery. There is the galvanostatic intermittent titration and the potentiostatic intermittent titration. There are some application notes in our website that you may download it. This one, I think it's very useful because the application notes are only direct information. And this Metrohm white paper, what's called white paper 052, is a guide to lithium-ion battery research and development. Reza Fati is an employee of Metrohm AutoLab in the Netherlands, and it's a very good material. I like it very much. It has a lot of information from the basics to how to perform some experiments. So if you're looking for a material that just to give an introduction or someone who is not in the field of electrochemistry, I think it may be helpful. Glove box are important, and I would only like to mention that if you are working with a glove box to make electrochemistry, be careful with the connection with the AutoLab, so you don't connect the ground of the BNC connector, because generally we use BNC connectors to connect the potentiostat to the electrodes inside the glove box. And be careful with this connection so you don't ground the whole glove box and connect it to the AutoLab. So we have cables for this, both for the modular line and Bionic. You may look for us and ask. We can give quotations if you need it. And this is only the cell part, but I think I got to with my time limit here. But it's just examples of a coin cell. If you're working with coin cell, there is this holder from AutoLab, which is gold plated and a Kelvin probe. Redox.me has a lot of cells, and this one is a kind of an alternative to Swagelok type, and it's very interesting because it has a micrometer when you can control the force you are applying in your material. Here is the cell expanded, so you can see the discs that we use as the electrodes, and we can control the force. And there is even a kind of cell that has temperature control. So I would recommend you to go to redox.me and look for the cell. But for batteries, we have the RHD cell that is a partner that's a fully integrated solution with Metrohm AutoLab system and even Software Nova. They have a lot of alternatives to work with low volume. Some cells have 17 microliters. We have the best temperature control you can find. It uses a Peltier element, and we can go from minus 40 degrees Celsius to 100 degrees Celsius, very fast controlled. And you can make a fully automation with Software Nova and an AutoLab system. There are some application notes only about this RHD system. It's very nice. It's very to work with batteries and those applications. So you can see some here: determination of lithium-ion transference number, investigation of solid electrolyte interface, structure and kinetics, and determination of the temperature-dependent conductivity of a solid proton conductor. Those were all made with this kind of cell, which is the RHD cell. So with this, I end my presentation. So thanks for your presence. Thiago and all the organization from School of Electrochemistry, I thank you one more time for the invitation. It's very nice to talk here. I like it very much. I hope this presentation was useful for you. Sorry if it was too quickly and for the internet drop, but if you have any doubts, you may contact me or your local Metrohm distributor. We have distributors all over the globe. So thank you. And if anyone has any question, you may ask now.
Thank you, André, for all the help with the school, and send my regards to Marcelo too. help us and to support the school. It's very important to create all this environment for the discussion, and it's very important. Thank you very much for that.
You may count on, as Marcelo likes to say, you may count on us.
Oh, thank you very much. There's a lot of replies here in the chat to say thank you for the presentation. It's very interesting, and thank you very much for that. And as the questions were performed during the presentation,
okay,
and I would say thank you to you again, André, and I will go to our last speaker. Gabriel is here to give us the final lecture, and the idea is Gabriel will talk a little bit. Gabriel was already show here in the school. He was already presented here in the school, and the idea here is Gabriel will talk about nanoscale electrochemistry techniques, considerations, and applications. Thank you, Gabriel, to accept again the invitation to show the now research results, and thank you for that.
No worries. Thank you, Thiago, for the invitation as always, and thank you both, Vitor and André, for the amazing presentations that I'm following now. I'll try to share my screen. Let's see if it works.
It's perfect.
Cool. I will try to monitor the chat as well at the same time, guys, if I can. So if there's any questions, I will see if I can see them. Okay, now I have. Okay, so this talk is going to be a little bit different than the other one that I gave. I think it's going to be more focused on the results that I have been, or the work I have been developing during my postdoctoral stage at the University of Warwick. And I think it ties very well with the ending of this school, because now we're moving towards a different length scale of electrochemistry. We talk a lot about techniques that are bulk techniques in a sense. They'll have big electrodes, and we're measuring the big electrodes in solution, the average response of that electrode. And now we're going to dive into more of an area that we're looking at that nano interface. And a lot of things we talk about, especially if you remember from my talk about this difference between homogeneous and heterogeneous reaction. I talk a lot about that interface that you guys focus massively before, the heterogeneous aspect of it, the interface between the electrode and solution. And most of those techniques, as we'll discuss, they always assume if you do a CV, for instance, of a gold electrode, that we're doing just the whole surface of the electrode is uniform and behaves as the same. And we know that for most materials, that's not true, right? As long as you tailor the length scale you're investigating, everything's heterogeneous and there's variations in its behavior. And there's a family of techniques that are able to investigate those heterogeneities and those different behaviors. And I'm going to introduce you to 3 of those techniques quite briefly. I don't think we'll have time to go into the mass transport aspects and stuff like that, although we might mention, and show some applications and why this could be interesting for you. So I think I said that before, so that's my contact if anyone has any questions. I know we're short in time, so please feel free to send me an email or tweet or anything like that. And as a disclaimer, as usually before the talk, I'm going to present in here slides with results, and then that they're definitely not recorded by me, they're recorded by students. I'm just the talking head here. They are definitely the experts and specialists that are on the bench. I'm just more of a supervisor in a sense, and I help them troubleshooting, right? So that's essentially the life of a postdoc. So before I started, I'm just going to put my pointer to laser point and go. So I like before starting to show where I come from. So I told you guys I'm University of Warwick, I'm a researcher there. So that's the United Kingdom for people that are not aware in the map. And I think United Kingdom, University of Warwick stays in England, is one of the 4 countries that makes the United Kingdom. And there I'm staying in a city called Coventry, which is a city exactly in the furthest part from the sea that you can be in a tiny island. And just bear in mind that the whole of the United Kingdom is the size of the state of São Paulo, right? So this is quite small. I work for a group called the Warwick Electrochemistry Interface Group. It's a group led by Professor Patrick Owen and Julie McPherson here. Patrick's my direct PI, my principal investigation, literally my boss. And this is a kind of an outdated picture because of COVID. We couldn't get together and take a group picture, but it was essentially the composition of the group at some point. So it's a big group with a lot of different people working in different areas. It's multicultural, multidisciplinary in a sense, because we'll tackle different cases. And it's very nice. It's a very place that I really like to work. And from at least according to my book, they're all great people, amazing scientists. And we're very active in the Twitter. So I encourage you guys to follow to keep up with the latest production of those people. Okay, so why should we bother to work in the nanoscale? Why should we just be happy with just have a big electrode and recording CVs and having that average result. Oh, I mentioned already that every time we do this average, even if I have like a gold electrode and I record a CV on ferrocyanide or HUHEX or whatever is a well-behaved redox couple, I'm getting a profile of the CV that you guys are all familiar with, but that's just the average of the entire surface, right? I'm not sure if the surface at the macroscopic level actually behaves like that. So if you imagine, for instance, about the Warwick kinetics, we have a rate constant, the K0, I can get a CV of a big electrode and get a value of K0, but is that value of K0 representative of every single part of that electrode, or it's actually an average of the entire surface? So most materials, this is kind of like, it's a gut thing that we have. Like if I ask you, like, are most materials heterogeneous? You're probably going to say, yeah, they're all heterogeneous. But it's kind of like things we know. If you look something with a microscope, it looks much different than if we look with our own eyes, right? So this is kind of intuitive for us to think. And it's real as well for electrochemistry. And here I'm just taking a few examples from papers using those techniques we're going to discuss. But just the fact that those techniques, they are able to map those chemical or electrochemical properties and show that they are quite different and they're quite heterogeneous. So here, for instance, just carbon steel, and we're looking at hydrogen evolution reaction, which some studies tying that to corrosion. And this is a map of the crystallographic orientation of that surface. And this is the same map here of the current of the hydrogen evolution reaction, just showing that different areas perform that reaction very different, and there's a correlation with that crystallographic orientation, sorry. Same thing for semiconductors, molybdenum sulfide, the same reaction. You can see there's a drastic difference in activity. This is the current, with yellow being higher currents on the step edges than on the plateaus here. If you go to graphene, and Vitor mentioned about graphene, for instance, for supercapacitors, which is still apparently something that's coming. And graphene was supposed to be part of the materials, and it is in a sense, but also graphene has a lot of heterogeneous reactions. So this is just an AFM of like a bunch of leaves or layers of graphene overlaid. And this is the here the reduction of hexamine, which is a very well-behaved redox couple. And we can see that it's quite heterogeneous throughout the entire surface. And this is a very small scan. This is a 30 by 30 micron. So you can imagine that there's a big heterogeneity to this, but if you record a whole CV, what we're getting is just this average information. And again, you might claim why that's important if the only thing we are concerned about is the average behavior, right? Because that's the final application. But in fact, if you understand, I think there's two sides for these questions. One of them is, if you understand there's the scientific knowledge and curiosity that we all have, and we want to answer some questions. And also the other one's quite important is that if you understand the intrinsic properties of parts of, for instance, crystallographic orientations, we can have this bottom-up approach to develop materials and tailor their properties to our needs and our desire. Instead of just counting that's going to be the average, maybe we can elucidate those properties, and that's now becoming an engineering problem. If I know that this given crystallography gives the appropriate material properties that I want, now it becomes an engineering problem. How to develop a bulk material that has mostly this crystallographic orientation, right? So I think that's quite important. And because I'm going to show here some results in regard to that here, I was going to mention as well that the double layer is also not homogeneous, right? And this is something that we talk a little bit about with Susanna and Vitor about the double layer structure. And this is much more like in a small scale, right? We're talking about few nanometers now, but also the distribution of species on that double layer is not homogeneous throughout the surface. And that gives rise to what we call surface charge. So species have different surface charges that are heterogeneous along that surface. And we can actually probe somehow that and actually see the charge that the surface has, because we're just probing the double layer. And also there's some new papers now that are just claiming, and I think it's true, of course, that the double layer is not static. It moves with time. It's a dynamic process, and especially for biological materials. So this is just an image, for instance, from hair scales. Those are just AFM. And that's just a charge map, something that we're going to discuss about. But it's a technique that can actually show us the surface charge. So this is in millicoulombs per square meter here of the surface. And you can see that there is a distribution that just mentioned that this just highlights that the double layer, the EDL there, it's not homogeneous, it's quite heterogeneous in a sense. So I like to make an analogy, and hopefully I convince you guys the importance of looking at that. But my analogy, which André pointed that every analogy fails at some point, and I do agree, but I think it's useful in the point, is that if I show you a picture, a photography, for instance, of something in very low resolution, you can barely distinguish what that is, right? And now so this for me is the bulk experimental electrode. I just have an average kind of information, and I can barely guess what I'm having. Now, if I start increasing the resolution, because I'm investigating the picture at smaller and smaller space, i.e. increasing the spatial resolution, I start to resolve a little bit better that problem, to a point that I get something that I can actually distinct like very characteristic features and differences, and to a point that I have a nice enough resolution that I can now understand more of the system. So that's the idea of coming from bulk experiments in electrochemistry and now decreasing the size and going to nanoscale, because now I can resolve the features of my interface, that heterogeneous interface, and understanding what's going on. We like a lot in Warwick to go one step further and to get more information, not only increase the spatial resolution, but use multiple techniques in the same sample to increase the amount of information that I have. Because you're going to see that all those techniques that we're going to talk about, they record different electrochemical information so they can probe different properties of that interface. And if I put them together, now I can compose a nice picture and I have a full understanding of the system. And here's the analogy of the picture, of course. Instead of only having one channel, now I have a full color picture. This is completely outdated because I can't be bothered to update this kind of family tree, because techniques just develop all the time. And it's a little bit controversial to name techniques. Some people sometimes they publish and they don't name it. So I'm not going to name anyone's technique. It's not to me to do that. But it's kind of a family tree of those nanometer scale electrochemical techniques. They all fall under the umbrella of scanning electrochemical probe microscopy techniques. So those are just techniques that use tiny, tiny electrodes. So we're talking about big gold electrodes at the beginning. Now imagine that I shrink that to the micrometer to nanometer size, and I use that electrode actually to bring it near to surface and acquire information regarding the surface. So I use that electrode to inquire about the surface properties. So in a sense, I'm going to use an electrode to probe other, if I'm probing an electrode, but I'm using an electrode to probe either the double layer of bacteria to the electrochemical kinetic of graphene or whatever I want to. So I just use a probe, that's why we call it scanning probe, and you can do a parallel here with thermal force microscopy, which everyone is familiar with, or scanning tunneling microscopy, which are both techniques that use a scanning probe that I'm going to move over a substrate and acquire information about the substrate. And information for AFM could be mechanical information, from STM could be conductivity, could be topography. And from those techniques, because they are electrochemical, I can acquire electrochemical information. So I can acquire, for instance, kinetics, electrode kinetics, or first the interface kinetics. I can acquire conductivity, I can acquire chemical composition, right? And now they are called microscopy techniques because we're gonna build actually a map of the surface, right? We're gonna go near that surface with that electrode, and we're gonna record electrochemical experiments at every single location along that surface, and then we can build a map of that characteristic. The three techniques that I like to talk about, and sadly we don't have much time to go very in depth, are three. I'm going to focus on three, and here they are just a cartoon of them. Is the scanning electrochemical microscopy, SCCM, the scanning ion conductance microscopy, SICM, and the scanning electrochemical cell microscopy, SECCM. Right, so they all rely on different electrodes. So SECM probably this is one to understand. So this is actually a very tiny solid electrode. So instead of having that big gold electrode, now I fabricate micrometer to nanometer scale carbon, platinum, gold electrodes. They're very small, and it is a solid electrode interface. I can do Fardac reactions here, charge transfer reactions. And if I bring the electrode really close to the surface, right, I can see how that surface influences the electrochemical response. So if this electrode is in bulk solution in the middle of a beaker, its response, its electrochemical behavior is quite well behaved. If I record a CV, I know how that CV should look like. But if I bring the electrode near to a surface, features of that surface, for instance, let's imagine that the surface is producing a species or consuming species, they're going to impact the electrode response, and that's how I can get information of the substrate as long as I'm close enough. The spatial resolution of this technique, I just point out, it's like tens of micrometers. Usually we can go to the nanometer scale, but it's quite challenging. So usually it's in tens of micrometers. This is important. I think Mauro talked about the kinetic transfer rate to you guys. And this is a parameter that just talking about the mass transport rate of those electrodes. And if they're in this Helm or in this size range, we're talking about this kind of kinetic transport rates, transport rates, which will be limiting of how, of the rate forward rate transfers, or the K0 for instance, about the Warm equation that I can probe. Right. So if you remember from our slides, I need to my system to either be limited by diffusion or limited by the kinetics, right? So this kind of limits how fast of a kinetic reaction or a surface reaction I can probe. So just bear in mind that all those techniques, they have their limitations, their considerations, and this is mainly because of the size of the electrode. If I show you guys a cyclic voltammogram recorded in one of those CVs, you're going to see that it looks like a sigmoidal shape, and I know that Mauro didn't cover that, but you guys were in my talk yesterday quite keen, and you knew about these mass transport aspects. So you can see that's what expect a plateau shape or a mass transport steady state limited case, and that's what we will record. I'd just like to point out the currents here, which are nanoamps, quite smaller than we saw so far, but I'm going to show techniques that have like much smaller currents than that. The next one we'll talk about is scanning ion conductance microscopy, and that's kind of an oddball here because it doesn't investigate any kind of Faraday reaction or happen on the surface, so no redox reactions. And I remember in Vitor's first class, he distinctly separated that to you guys, that there are two kinds of electrochemistries. There's one that you can investigate this charge transfer reactions, Faraday reaction, sorry, and one that you don't see the Faraday reaction, but you just look at like ionic electrochemistry. And that's essentially what a Symposium does. So instead of having a solid electrode in solution, I have a hollow pipette. In this case, a nano pipette. So this is a glass needle that's open in the middle and has hundreds of nanometers, if not less, of this opening. And I fill this pipette with electrolyte solution. And if I apply a potential between these pipettes, so I can just insert a reference electrode inside and against another one in solution, I'm just going to induce migration of ions to this very tiny pore. And this very tiny pore is a big resistor because it's restricting the flow of ions. And it has its own electrical properties because glass has its own electrical double layer on it. So it's going to change how ions pass through. They're not just going to be flowing freely. But more importantly, if I bring that really close to the surface, so if I bring a few nanometers from the surface, tens of nanometers from the surface, now the double layer that's developed on a substrate, and any substrate, any material in solution will develop a double layer, now it starts to impact the ion transport here because the gap's so close that the ions cannot move freely in and out of this pipette because they're going to sense the double layer somehow. They're going to be disturbed. The mass transport is going to be changed by the double layer, and I can use that to probe the surface charge. So SICM is characteristics that it probes ionic concentration or conductivity in solution, and we can use to probe the double layer and the double layer characteristics. I say that's an oddball because if I look at CV of an SICM, it looks quite different than you guys expect. It's just a line. It's not a straight line. So if I look very close to zero potential, it's a straight line, which I expect as a resistor because of a very small pore. But if I go to larger potentials in both ways, you can see there's a distortion from this resistance. And this is just showing that there is an asymmetric transport of ions because now the double layer of the glass, because so small, is changing the ion transport number here, but also the substrate, if this is close to substrate, also impact that. So I can start to infer and get information from a substrate double layer just by looking at how this current is deflecting. The last one I'm going to talk about is the scanning electrochemical cell microscopy, which has some familiarities between those two. It's kind of a mesh, I like to think. I know I'm pretty sure people are not going to be happy with that analogy. But just the fact that I also have a nanopipette here that I'm filling with electrolyte solution, but it's not in a bath solution anymore. I have a dry substrate. So this is one of the limitations we don't use, for instance, in biology. These we use for electrode characterization usually. So imagine this is like, I don't know, a graphene electrode, for instance. So I have this pipette loaded with some redox species here, and I just land this pipette very gently to this graphene electrode and I form a tiny meniscus here. And then what I can do is to perform electrochemistry. If I have a reference electrode inside this pipette and I connect to my substrate, I can apply difference of potential between those two and drive Faraday reactions here. So I'm essentially making a very tiny confined electrochemical cell. And we can go to tens of nanometers of spatial resolution here. We can have 20 nanometers tips that form usually 30-ish nanometers meniscus here. And then I'm recording electrochemistry at that 30 nanometer meniscus, right? Because it's small tip, it has a very high mass transport rate. So you can see that's better than the CCM for this, just for the size, because of tens of nanometers of size. It means which I can investigate much faster reactions of those. So if you remember of my talk, we're talking about the KF, for instance, I can, the Ford rate constant of the chemical step, I could investigate those more, for instance, here, or even the electrochemical step, the K0 from bottom warmer, I can investigate those in the top range, the top edge, or the limiting will be much higher for this case here. So yeah, and this is the CVs, how they look, and they look similar. This is one, it's just because I'm showing here for an oxidation, so why the current's positive, but you can see plateaus as well. But I'd just like to stress out the current level here, right? We're talking about nanoamps in CCM, and here we're talking about picoamps. So it's much smaller current. That's because of the size of the pipette. So, well, why is that important? How is that important? And how we'll apply that, those techniques? So the first example that I would like to show you is because I think it ties very well this problem of things not being exactly what they look. If we look outside, if we look at the macro scale, they look something, and then we zoom in at the nanoscale, they look completely different. So this is the case of the ITO. And André shows, for instance, the spectroelectrochemistry part of Metrohm. And there's a lot of spectroelectrochemistry that use ITO, indium flame oxide electrodes, because they are essentially transparent electrodes, right? We can perform electrochemistry in a material that's transparent to most wavelengths. So it's very cheap, usually. People use quite a lot. But there is a problem with ITO because if you record a voltammogram, so if I have a big piece of ITO, let's imagine I have like a 0.5 millimeter electrode, which electrochemistry terms, it's quite big. And I record a cyclic voltammogram there on a very nice reversible species like photanohexamine or ferrocene methanol or whatever you choose to do so. The CV is going to look like this is the red one here, which looks sort of nice, but you can see that there's a little bit inclined. So the peak distance is a little bit larger than we expect. But more than that, the peak current is not what we expect it to be, right? So this is just compared to a gold CV here in black, and they have the same area, same concentrations, same everything. And you can see they look quite different. And technically, there's no reason for gold and ITO to behave differently because ITO is a very high doped semiconductor, right? So it's almost metallic. So it should be, especially for those outer sphere reactions that we're looking here, it should be as fast as it gets, right? It should be just like gold. And the fact is it's not. We can see this behavior in the CV. And a lot of people, much smarter than I'll ever be, have thought about that back in the day. And they come to a brilliant conclusion. That's the fact that actually ITO, because the material that we deposit on the surface, we do either chemical operation, we can use butter. It's not 100% active, right? We have islands of activity in areas that are not that active because its deposition is not very uniform. And if you look at an SCM of ITO, that kind of ties nicely because it's a very rough surface to a level. So the idea is that we have a lot of islands that are active and parts that are not active. And overall, what this happens, the behavior that this results is an electrode that looks like to be a little bit like this sluggish kinetics. I know that Mauro said that quite a lot because Mauro likes this term. So the overall behavior is that sluggish is a slow electrode, even though every single part of those islands behave just like gold. It's as active as any metal. And I think this is a very fair assumption and a very brilliant conclusion to come, because that's how we can assess, right? We're just looking at the macroscale. But we do have now those techniques that are sort of recent that we can actually probe the activity of ITO at the nanoscale. And that's exactly what we did. And when I mean what we did, actually what Shagan did, he's a PhD student, final year work, brilliant student. And he used a CCCM, the technique that uses a tiny nanopipette. And here I'm just showing an SCM of a nanopipette, if you guys never saw. So these darker regions is the glass. This is the opening. It's roughly 22 nanometers opening. So he took one of those pipettes, loaded with, I think it was ferrocene methanol, if I'm not mistaken. And he placed an electrode. He took an ITO slide and he did an experiment we call a hopping scan, which you land this tip at different locations over the ITO, and in every location you record a CV, right? So you have this electrochemical area here. So my spatial resolutions, I'm recording information over this area of the meniscus, which is roughly 30 nanometer radius, and then he moves away and records CV. If you look at the SCM of ITO, as I mentioned, is quite rough, right? So that's why that heterogeneous. So I forgot to mention that this we call a heterogeneous accessible electrode. So this ties very well together with the narrative. And if you look at the CCCM topography map, because that's a nice feature of this technique, we can acquire topography together as well. It sort of relates, like you can see there is speckles of higher topography than the other. So it kind of matches. So it seems nice for getting a nice result. But more importantly, how does CVs look at every single one of those points? So I'm showing you guys here a family of CVs. Those are the first ones that I showed you on the slide talking about the CCCM. And they all look like we expected, right? They look like we have this plateau, we get to this steady state current. Some of them have different currents, and some of them have different of those inclinations. And this is already hinting to us that there's different kinetics on the surface, right? Because we have something here that's quite fast. Remember on my talk yesterday that I like to think this is a thermodynamic in a lot of, because no, it's not this, but it's the amount of energy I'm providing to the system and the kinetics aspect. So there's a system here that I have to provide a little bit of energy and the reaction happens really fast. Another one that I have to provide a lot of energy, and even so the reaction happens very slow, right? So this hints to us there's different kinetics on that surface. On one of those scans of this area, and this is almost a 10 by 10 micron, we have more than 7,000 voltammograms, so more than 7,000 pixels in this image. Every pixel, we're assuming that's 15 nanometers. So assume that the pipette meniscus wets a little bit. There's not a single one pixel. Actually, I think there was 4 pixels that didn't give an electrochemical result. So every single one of those pixels, we could record as CV, right? So those are snapshots of, because as this is a CV, I can actually map each potential. So those are just snapshots kind of from a movie that I can map each potential to the surface area. So if I vary here in negatives, in a negative potential where I should not see any oxidation of the species I have in solution, so it's roughly here, I can see that everyone has a zero current, right? So the entire surface has no current as expected. As soon as I start increasing the potential, and it's quite nice to see here around 0.4, I have a massive contrast. I have areas that have a large current here, so 3 picoamps or more, and I have regions that have 0, right, still. So this is just alluding to the fact that I have regions that are quite fast and regions that are quite slow. So at a given 0.4 volts here, if I put a line here, I have regions that are already in steady state and regions that are just getting there still, right? But again, none of the surface is inactive. And of course, if I go very, in this case, I'm going very positive, I'm getting to limited steady state to everyone. So there's a different current here between 2 and 3, but everyone is active. So can we quantify and can we try to understand why is that difference in the CV behavior? And we can. I don't remember, and I apologize because I wasn't in all the talks, if people talk about half-wave potential, quarter-wave potential, or three-quarter-wave potential, but those are nice quantitative numbers that we electrochemists, we can use to actually quantify. So this sluggish behavior we're talking about, so how fast and how slow the surface, we can actually put some numbers to that, and we can look at those as markers, right? So especially if you look at the difference between my 3/4 and quarter potential, that's going to show how sloped it is, that CV, and that gives a nice indication of how sluggish or how fast it is, that surface. So what we did for every single CV of those more than 7,000, we run to a script which we get for every single one of those, the half-wave potential and the quartile wave potentials, and we make the difference. And if you look here, this is just a histogram, the distribution of the half-wave potential and the quartile difference. It's quite nice to see that it's a very broad distribution. I have some things that have a very small half-wave potential, near to what we expected to have, for instance, for gold, and these were comparing for gold. So we have like places which have a very high half-wave potential, but we have also places that have a very slow half-wave potential, right? So they're very far away from the expected. And this is just half-wave potential for this reaction is expected to be in 2.4, I think, or something like 2.4 something or nearby. So have things are as reversible as gold. Most of it's not, but we have areas that are very, very slow, that have the half-wave is very shifted towards a more positive. If you look again to the quartile and three-quarter potential difference, as I mentioned, that's I think more informative even. We can see that on gold, we expect this to be near the 59 millivolts here, and that's dead on the distribution of gold if we do the experiment in gold. But if you look at the ITO, there's a very broad distribution, and it's not a monotonic one. Like we have at least 2 separate groups here. So have an average population here, which is a little bit slow, and it goes towards the second group here, which is quite slow, right? So this is a way that we can quantify, and this would just normalize the peak currents here, so they all scale at the same range. But we're just showing those 3 cases that we put here. So we divided this histogram in those quartile waves or the delta E potential here. And we can see that we have faster groups that are similar to gold. Gold's black line here is barely seen. And then we have these 2 other groups, slower and even is lower than the other. So that's all nice, but we have a map. Can we try to, I don't know, map this somehow, try to understand? Because so far we just get a number. We know that it's 100% active, but can we go one step forward and try to understand and correlate how that ties together with that heterogeneous accessible surfaces where I have those islands of activity and a part is not active? So we resort to simulation, and Guy talked about COMSOL yesterday. I managed to get a glimpse of it, so it was a very nice talk. And we resort to COMSOL once more. It's a very simple model, which we use transmission electron microscopy to get the geometry of this pipette, and we draw in COMSOL. So I'll show you how to draw the simulation domain. So actually have the true geometry of the pipette. We make some assumptions. So this is the pipette and this is the meniscus. We make some assumption on how the droplet looks like. We impose a boundary condition here, which is just about the Warmer kinetics for that electrode, right? And what we can do is now run some CVs for that, the boundary conditions for varying values, for instance, of alpha and K0, and see how they change and try to match them to our experimental data to get now even more quantitative. Although the delta E quarter and the E half potential shift are nice to have an idea and to have a visualization, they are not quantifiable numbers in the sense of actually a proper electrokinetics. So what we do, this is just a flow chart essentially of how we do. we have our simulation domain, we build in console, we have our boundary conditions, all the concentrations, and then we run a bunch of simulations. So for this paper, 191 combinations of different K0s and alphas, and that provides a family of vortamograms for those different values. What we can do now for those simulated data is do very similar to what we did to the experimental one, and is to find the values of three-quarter potential, the quartile potential, essentially the half-wave potentials for every single one of those, and build a working surface, a 3D surface that has values of alpha, values of K0, and in the axis we have the half-wave shift from the formal potential and the quartile potential, the delta quartile potential. Right, so we can take this now 3D surface, we've correlate all this data, all those parameters, and overlay and interpolate all experimental data to that surface to try to recover values of alpha and values of K0 from that experiment. And from that, we can now plot a map of alphas and K0s from that surface and try to understand the kinetics actually of that surface. So when we do that, we interpolate, and of course there are outliers here, there's interpolation, there's points that we cannot actually get to the model, and that's just an approximation of the model. But if we look at the K0 map and the alpha map here, we can see that there's a broad distribution. This is in log of K0, of course, but we do have regions that are quite fast, and we do have regions that are actually quite fairly slow. But again, 100% of this is active, besides I think 3 pixels that are marked in red here. Alpha map's the same, although the distribution is nearly half what you'd expect for this kind of system. And I think maybe it's more informative if we look to the maps, they look nice, don't get me wrong. I quite like the fact that we can actually map this. And one could do an argument that this has some correlation with topography, but if you do just a line scan here and we try like the same region to get K0 values in topography, there's no correlation there. It just look like noise. There's no correlation at all. We did that for a few lines. So there's no correlation with the topography. But if we do a histogram distribution of those values, we can see again, they'll have some pixels are quite fast as gold, as we expected here. When a K0 is very high value, this is log K0 again. And then we have this, which it looks for me like almost 3 groups here. We have a very slow one, we have a broad one here, and then we have a very sharp one group here. So the average behavior is roughly here. So it's a fast, but not fast-ish. So this is the average K0. Far from expected, I think I forgot to mention, for conductive materials, we assume that K0 is at least 1 centimeter per second or more, like for all conductive. It depends on the transport rate of your technique, what's the top end that you can simulate or you can detect. But anything 10 centimeters, 100 centimeters per second, that's all going to be very reversible, very fast. But the calculated one here is 0.08, which is off what we expected, just showing that's a slowish surface than expected. With a group here very slow. Alpha is in the ballpark of 5, so not much comment on that, especially because alpha is hard to argue why it would not be alpha in this case. Why is that now? So how do we tie that with the heterogeneous accessible electrode model and the behavior we see in the bulk? The answer is that we don't, and that's the biggest problem for us so far. We're not sure how to explain, because it's not that the average K0 that we find from bulk is exactly this. They differ a little bit in order of magnitude. The other one we expect to be a little bit faster than that. So the explanation is that we're not sure if we're inducing there's some experimental bias here. We don't think there is. We think we're actually changing a little bit the polarization of the conductivity of the ITO at some point. But the take-home message here is that actually ITO is 100% conductive, right? It's not conductive, and it's far from being as conductive as a metal. So there was a metallic, almost a metallic semiconductor, and we did it for a few samples. A few samples are better than the other. High quality ITO is a little bit better than this, but it's the fact that it's not exactly metallic. It behaves a little bit differently than you expected, but it's 100% active, right? So that model of the heterogeneous axis, it doesn't fit very well, and it doesn't fit because at first we can only look from afar, and now that we can close in, we see that the properties are quite different than what we expected to. So that's the power of those techniques. That's why they allow us to do, and they provide us means to actually see that kind of nanoscopic behavior and actually see to the real surface. An argument could make that we could even try to go down with some techniques and do the atom level. And of course, there are efforts towards that direction of people trying to do single atom catalysis and stuff like that. But it's the point that, and that's again the take-home message, is that the bulk behavior is quite different. It's not a representation of actually the surfaces, and surface can be quite heterogeneous, right? So that CV that we got, it's a mixed match of all those K0s happening. And if you do the bulk experiment and get a K0 from that, we're going to get a K0 that's actually different from any of the K0s we see on this distribution value here. So are other materials the same as well? And just to point out, those slides are all on probing surface kinetics and facial kinetics of CCM. We're going to kind of build upon it. Then we're going to go to probing chemical composition and primary surface charge and so forth. So are other materials like that? Yes, they are. So just because we talk about graphene, and that's a work led by Deng-Chi Liu, was just published in Nature Communications. So it's a brilliant work from a brilliant group of people. It's a large collaboration, which I took a very, very small part in it, to be honest. But it's amazing that we're able to see, using the CCCM, the same technique, with that tiny pipette full of electrolyte solution, we could approach the graphene layers that were deposited over copper and try to check the kinetics, the surface kinetics of that electrode of the technique. So essentially, we did the same thing. We record CVs at every single location of a sample of graphene, which was composed by monolayers, bilayers, and multi-layers of graphene. And again, just similar to the ITO, we got a lot of different CV behaviors, right? So we can see here for the monolayer and the bilayer, how they are slightly different. I think my mouse, okay, it's back. So how they're slightly different. So we get a mix of behaviors with different, again, of those different kinetics, faster and slow kinetics. And we couldn't understand exactly why, since graphene should be this amazing conductor. And it's just like a sheet of graphene on top of water. We're talking about going from one atom to two atoms on top of water. And we can characterize how many atoms by many techniques, including Raman, is possible to do it. And how to explain that? How to explain, for instance, that monolayers are faster than bilayers, and which are faster than the multilayers. So we resort, again, to the same kind of simulation, the same kind of working curve to recover values of K0s. And we did recover, and we can see actually that monolayers are quite faster than bilayers, and which are quite faster than multilayers. So we can actually now quantify, and we try to explain why is that. And that's why the brilliant people, even more brilliant people in this paper, come to this group that makes simulations from group from Warwick as well. And then he did molecular dynamic simulation to, DFT simulations to calculate the potential across that graphene sheet. And you can see that there's a drop. There's actually the other layers of graphene is screening the potential they're seeing. So I'm applying a potential to the copper, which is the electric contact. And the potential that my solution sees is screened by those graphene layers. And that explains quite well why this kinetic. So even though this is an almighty conductor and it's very fast and it's very thin, it's still able to screen potential quite a lot, to a point that I see different kinetics for different leaves. And this, I think, has a nice implication. There is an implication in electrochemistry field, because now I understand it's kind of a diabatic versus non-diabatic in electric transfer in graphene. We kind of pin down what's happening, but practical applications as well, because we know that, of course, it's impossible to have a single layer of graphene that's as long as it takes for making a supercapacitor, but there's an impact on the amount of multi-layers or bilayers they have. So we have to bear that in mind and be able to engineer materials properly, because this affects the property quite a lot. And once more, we're not going to be able to see that if it weren't for those techniques that can do electrochemistry resolve in space. Moving on from probing electrokinetics with a CCCM, we're going to still stay with a CCCM, but now we're going to probe electrochemical composition. And this is a brilliant work as well, done by led by Dimitris. It's a PhD student and work as well, in collaboration with Frederick's Knuth group in Paris. So it was also led by Paulo, another PhD student in Paris. And the idea was to use a CCCM, and now a new technique that was developed in Paris that's essentially a interferometric technique. We can look, so if you use ITO as a substrate, we'll land a pipette on the top, as I'm looking here, and then I have an inverted microscope. I can make this microscope be an interferometer detector that I can actually look at the interface of the graphene. So any chemical reaction, any deposition that happened there, I can actually visualize optically. Also, I have the electrochemical information. So we pose to do that, to investigate a few systems, including the position of nanoparticles and the position of crystals, in this case, calcium carbonate, and try to see if we can look at those reactions, but not only look at those reactions, try to map chemical composition within that cell and see if we can actually see, in a sense, that chemical composition. So this is just a brief explanation of how this works. So again, it's the CCCM probe here, right? So it's this, the pipette filled solution that I landed on an ITO glass substrate. That's my electrode. And I have the microscope here, which is just visualizing from the bottom. So those are images that we see here from the bottom. So this is quite zoom in. So this is the footprint of one of those meniscus here. So this is 500 nanometers across. So the meniscus is a little bit smaller, it's 400 nanometers. And we can do exactly the same thing as we did for the ITO or for the graphene. And we can hop this along the surface in different positions, and we can have an array. So we can have a high throughput. We can investigate a bunch of areas of the same electrode and get more information. So the first thing we did, because it's ITO, and ITO we saw already that's quite heterogeneous. So would that heterogeneity impact somehow our chemistry and our chemical distribution? We do some background experiments where we record CVs, and as the CV we recorded, just electrolytes, is just potassium nitrate. We can see a very flat CV until we get here, which is just electrolyte discharge, so just oxygen reduction and hydrogen evolution reaction. If you guys were paying attention now, and you pay attention to the whole school, you will notice that something happening here, right? Remember, potential energy I'm giving, speed of reaction. So on my forward sweep, I have to give a lot of energy for the reaction to happen, and then it happens with a given speed. But when I reverse the sweep, so in my reverse sweep, I need to give less energy for the reaction to still be happening quite fast. So this crossing point, this is just a telltale sign that something happened in my surface and I'm modified, right? But here I just have potassium nitrate. So what happened, and we think here is just, we're just reducing the ITO on the surface, we're just making smaller parts of ITO. And it's important to realize that, because this sets kind of a potential limit window to ITO where I can use. And besides that, it's going to be the substrate response. And because we saw the ITO is quite heterogeneous in the past examples, this limits quite a lot of the application, because this behavior is not all in all the same areas of ITO, right? It changes a little bit of space. But it's quite nice that we can see a feature. So those are the images. You can see that I have absolutely nothing until we get to very negative potentials. And there's a feature that appears. And even if I flip the potential, the feature is still there. So pretty much it's a nanoparticle that forms and that I cannot reverse. And we can track the intensity of that this optical feature as well with the charge that I can integrate from the CV. So it's quite nice to see that I can correlate those two factors, and it can actually have a visualization of a chemical reaction happening here. And that gives us a lot of confidence that we can use this technique to map chemical compositions and chemical gradients and to investigate reactions. One reaction that we'd like to investigate was the silver nanoparticle growth on, and that's a lot of people have done that before, and we did by applying a potential here, and we can see there's a feature here wants to apply a very chaotic potential on a solution containing silver nitrate that we form a nanoparticle, and we can track the intensity here. And if we just calculate by the transient of current the size of the particle, and we compare with this thing here, we can see that we can track the formation of the particle if we compare with the intensity from the charge from almost nothing to until 120 nanometers, showing that we actually, like, we can see stuff that's below the diffraction limit of the technique, expected as a diffraction kind of interferometer detector, but quite nice and give us a lot of interest. And why I want to see that, I told you that we're interested on the distribution of chemical composition on species, is because actually we're quite keen to see, let's see if those videos will play. So this is the raw image you can get, and this is the treated image, which I know it looks a little bit like magic. I'm quite skeptical sometimes, it's quite amazing. So this is the deposition of nanoparticles, and we can see the formation of at least 4 nanoparticles. And then one of them does disappear, and the other ones seems that they're getting together, they are coalescing in the same one. So it's the ability that we have now to try to understand the chemical composition distribution over that meniscus and try to tie that with the ITO heterogeneities. You can make an argument and make a point here, but to see why those nanoparticles, they are moving away. Are they oxidizing to the potential? Are they just getting out of the plane? Why those are moving together? And maybe we think that might be tied together with some concentration gradient somehow, or some kind of mass transport that's affecting. So this is quite preliminary data that I'm showing just because I think it looks quite cool. We went one step further looking at chemical composition. So let's talk about a reaction that actually changes quite the chemical composition, and that's the crystallization. And our group's quite big in crystallization, and there's an amazing postdoc here in McPherson now that he deals with all the crystallization problems, and he's my go-to guy for crystals. And we're talking about the crystallization of carbon, of calcite, in solution. And what we're trying to do here is to have a pipette, would have a solution of calcium carbonate that's very much undersaturated. And we land to the ITO, and on the ITO, we swing the potential, so perform ORR, which is going to consume some protons. And by swinging the potential, we're driving the solution that's undersaturated to become saturated at some point, and we can see those crystals growing and see if there's any kind of spatial distribution and specificities of where those crystals grow, because now we can actually visualize, and that might tie together with local chemical composition, since the nucleation energy should be similar to any one of those crystals in a bare surface. So just very, very quickly, I think this video is going to be in the loop. So this is a video of experiment. We perform the potential swing on different potential, the pH swing for different potentials. So you can imagine the more cathodic one, the more ORR I'm performing. So I'm going to drive the reaction faster. Those are just snapshot of nanoparticles. So if I'm very mild here, minus 0.4, I'll barely see something that's very very, very small. If I go a little bit harder on the driving force, I see more nanoparticles. And if I go really, really harder, I see much more. And because we're still far away from that limit that we impose on -1.2 for the ITO reduction, we're seeing that this is most likely crystals and not ITO, although it's hard to be sure. We did some Raman too, and we do have the characteristics of what's expected from the calcium carbonate deposits. But it's quite nice that we have this correlation, but we saw no spatial distribution, right? We saw, as we expected, that everything be quite averaged out. And this is a kind of a 4 micron meniscus or something like that. So it's kind of a confined environment. So we decided to go a little bit further and look at this larger tip. So this is an 80 micron wetted area essentially. And we try to see how crystallization happened, if there's any spatial distribution. And just from those snapshots, I can clearly show guys there's a different space distribution, of course, different potentials, different timeframes. But I think if I show you the videos a little bit nicer. So we're applying a potential here to reduce oxygen. So we're swinging the pH, and you can see at first, not much happened. No, sorry, I think I have to plug it. So things happen at first, mostly at the edges, and then the entire surface cover at the edges, I have larger crystals being forming, right? So those plots here were just, so if I just go again, because I think those plots, they can be quite informative. They're just showing the radial position here of the feature. So from zero is the center here to the edge of the pipette, and when they happen of time, this is just the current transit. So there's clearly spatial distribution here, and when the event's happening on the size of the crystals we get. And of course, the first events, they have longer times to grow. So that's why the crystals are big. So there's a nice visualization here of chemical composition of the solution. And then we can actually probe as ECCM, we can actually visualize, and we can use finite element, we can use computational simulations, finite element method again, COMSOL, as Guy talked yesterday, to try to understand why is that. And that's exactly what we did. And the amazing thing about the system, I think it's quite beautiful, is that an interplay about among a lot of things. So I'm driving a reaction in the surface that's pretty much homogeneous overall, right? I'm just driving oxygen reduction reaction. All the surface is going to be doing oxygen reduction reaction. But now I have an interplay of the mass transport from that pipette, which is quite high and is bringing fresh solution to the middle of this pipette. So it's buffering the effect. So even though I'm consuming protons here, I'm transporting a lot of protons. So the center of that, my meniscus, my footprint is buffered by that transport. And I also have the transport of CO2 from solution to that meniscus wall, which also buffers around this region here. So the only area, the first area that can get nucleation, the area that I have that pH swing, is at that halo a little bit further away from the edge and further from the center. And it's exactly the one that we see happening right here in the video, if I can play it again, right? So this is the area, the first rich supersaturation, because the equilibrium between mass transport from the pipette and the mass transport from CO2 from solution. So I think it's quite beautiful that we can actually simulate, but we can actually visualize as well the chemical distribution, and we can use those techniques to try to probe that in a different way. Moving forward, I'd like to talk a little bit about biology. I still have a few minutes, and I'm aware that I'm talking quite fast. I apologize for that, just because we have a lot to cover. I'm going to delve a little bit in biology because I think it's straightforward for us to think of this heterogeneity behavior, or in biology as well, but we always think of electrodes, like we're mostly electrochemists. So even though I showed the ITO is heterogeneous, you guys probably saying like no biggie that I imagine. Graphene may be a little bit more like sketchy. You expect to be completely homogeneous, and we're just saying that's not necessarily. But biology, I think we expect it to be to a level very heterogeneous, and we do a lot of biology in our group, and that's a brilliant work did by Kelsey Kremen. She's also a PhD student in our group in the final year, and she set herself to check the charge distribution. So now we're moving towards the Symposium, the technique that probes ion conductivity and can probe the double layer. And the idea is to try to understand what was the charge distribution between two strains of bacteria, a gram-positive and a gram-negative one, and see if there was any surface charge distribution. And that could help us explain why different strains of bacteria adhere differently from different biofilms, right? Because there must be some kind of electrostatic interaction at that aggregation of bacteria. And I'm just quickly passing through. This is the difference between gram-positive and gram-negative cell wall, cell envelope, right? One of them has this polypeptide glycan kind of like very permeable membrane that can actually is a polyelectrolyte in a sense. And the other one has this second lipid bilayer, which is very insulator, and there's no transport of ions through that. And the nice thing is that we can see a massive change in surface charge between those two species, right? And we can see here, so those are the graphs of surface charge and surface distribution. They do have a difference between them. The surface charge is quite heterogeneous over a single bacteria. So each one of those individuals here is one bacteria, and this is just a topographic map, and this is the surface charge map we can get from this technique. And more than that, not only the surface charge is different, we can now sort of trying to probe the transport properties on this interface, on this polyelectrolyte. And we did that. We have a console model that accommodated for that. And we can actually see that part of what we're doing is probing this polyelectrolyte. And Janine Masrol has a nice work on that she uses ICM to actually probe transport on porous materials, and just proving how SICM can be very powerful to probe ionic transport in a sense. So you don't get kinetics of electrode, you're not seeing for dike reactions, but you can get distribution of ions, you can get surface charge, you can get transport properties. We can do a little bit more of this ICM, and I'm following in Kelsey's work and also on Gauss's work, although I'm not showing necessarily her work right now because it's still in preparation. Kelsey's a little bit more mature in that stage, is that we can use SICM not only to probe, but also now we can use to disturb the chemical environment at the nanoscale and try to see with other techniques and optical techniques now. So this ties a little bit back to the IRM, to Dimitri's work. We're coupling now optical techniques with biology, which they're the gold standard for biology, to try to use now the electrochemical techniques to disturb nanometrically or on the nanoscale or the microscale the chemical environment, and see how cells behave, and see if we can see any heterogeneity on that cell behavior, right? Because the parallel for cells, if you look at the big electrode behavior, right? If I have a big gold electrode that I do a CV, and I show you guys that we go to the nanoscale, the behavior is completely different. For a cell would be I have a Petri dish, a full grown, 50%, 60% confluence Petri dish, and I do a plate reader experiment, and then I have an average behavior that I think the parallel to go down is go at least to the single cell, to the single individual. Although on the SICM, we show that we can see within a single individual here characteristics, would be nice enough just to see if different individuals behave a little bit different. And that's what we're doing with HeLa cells, with cancer cells. We're using a SICM to disturb the chemical environment, or to disturb the chemical homeostasis of the cells by two means. One mean with Kelsey is to deliver acid to that cells. And this is just a common cell simulation here. So this is geometry representing the cell and the cell wall. This is our pipette. And we just apply a potential to change to deliver protons here in solution. So you can see that when we flip the potential is when, as soon as we have the change in color now, we're just delivering protons and we're just changing the pH around the cell, right? And we can calculate the console, we take into account the equilibrium from, of course, the media here. Nice thing of doing that is that I'm delivering by migration. So I can, with different potentials, control the amount I deliver. So this is just a plot of the pH in a distance here. So I'm looking at this line here. So you can see with different potentials, the higher potential, the quicker I swing that at that pH. And I can, of course, quantify that. And what Gauss is doing, which I'm not showing here, but she's doing this similar thing, but actually permeating cells. So we're trying to deliver like dosing very small DMSO and see how different cells uptake, for instance, different pharmaceutical compounds. So we can deliver DMSO and we can deliver any like biocides. So we can deliver DMSO together with silver nanoparticles, for instance, which are known to kill cells and kill bacteria, for instance. And we can try to do that in a single cell level because it's quite concentrated. Although it changes the color, it doesn't change that much the pH. So it's very near the cell that we're changing. So we can challenge a single cell in a Petri dish and not interfere with the other. And then we can start challenging other ones and see how they behave. And this is exactly what we have done with the pH change. And although I just said that we don't necessarily see the neighbor cells are unaffected, they are a little bit affected. So those are just dyes that are just reporting the pH of the cell. So you can see this is our target cell. And when I start delivering, this target cell goes, it loses fluorescence quite a lot. So this is the beginning of the experiment. As soon as I start delivering, it loses fluorescence. The neighbor ones a little bit. And if I plot intensity here, you can see that this is the liver cell. It lost a lot of fluorescence. The neighbor ones a little bit, but the other one further away, they don't, right? This is just a normal trend. It's just sort of photobleaching of this dye. So we can actually control and localize challenge the cells and now see how the different cells with the different morphologies, we can use different fluorescence markers for different metabolic properties of the cell. We can now see how those correlate, like does a cell respond quicker to this pH challenge if they are challenged another way, if they are redox imbalance, for instance. And that's what we're setting ourselves to do. And that's the same thing we're going to do with the MSO. I'm going to move now to another technique on my final 10 minutes, which is the one I haven't talked yet. The one that I started that was the easiest one, which is the scanning electrochemical microscopy. And we're going to talk about the same, now the idea of probing chemical composition over individuals. So we probe chemical composition with IRM and SCCM, and we actually visualize it and simulate it. But now we're going to use in a more of an electroanalytical sense. We're going to use a tiny electrode to probe the chemical composition around a substrate. and try to infer, because it's biology now, some properties of that organism. So we're stepping a notch from single cells, and we're talking about a group of cells. So we're talking about roundworms and C. elegans here, which they have a very finite and controlled number of cells. And we're going to investigate the respiration of it using scanner electrochemical microscopy. This work was performed by Dr. Carla Santana Santos. She's an amazing scientist, but she was a PhD student, an amazing PhD student in Mauro's lab at that time. And the idea is that she could use a platinum electrode, a very tiny electrode, which we can barely see here from this inverted microscope view. And she could approach to this nematode, this worm, which is alive, is just anesthetized. And what she can do is to perform oxygen reduction reaction, this platinum electrode, and near the animal. So if my UME is performing, my ultramicroelectrode is performing oxygen reduction reaction, remember we talked a lot about that yesterday, the current is proportional to concentration. If I bring near a substrate that's consuming oxygen and respiration consumes oxygen, there's going to be less oxygen around this nematode, around the cell, hence my current is going to be a little bit smaller, right? So that's exactly what she did, and she actually mapped a whole nematode. So this is just the map of the current, and just for us here, they're all normalized to avoid any kind of drift. But just bear in mind that higher currents mean less respiration, right? Because I have a higher concentration of oxygen nearby. Smaller currents means that I have less oxygen. That's why I have a lower current. So we can see that from the head to the reproductive area, the vulva of the animal, there's quite a difference, with this area here having the lowest concentration of oxygen, meaning the highest respiration. So we set ourselves to do a lot of experiments, and I mean a lot, and I was lucky enough that I didn't take part of any one of those because I was only doing the simulations. And Carla did a lot of experiments in a lot of animals in different conditions, even over pharmaceutical challenges, to try to see if there was any difference in respiration behavior. And my part, of course, was to try to simulate and try to convert those values of current in OCR, which is the oxygen consumption rate, which is just a hallmark of how much an animal is respiring or not. So from all those results, we could see, first of all, that the head region from the animal, it does breathe, but it doesn't respire that much. And the vulva region, the reproductive area, it respires quite a lot. And this, of course, alludes to the cost of reproduction, right? And we did this in collaboration with the biochemistry department as well, from the institute with Alicia, a professor in the department, and that's something that she brought to the paper as well. That is the cost of reproduction. That's quite high. And what we set ourselves to do is to try to knock off part of this reproductive system. So we knock off, this animal is an hermaphrodite, so we produce eggs that they just hatch with animals. So first of all, we make the animal just produce eggs that are not viable, so never hatch. Then we made the animal to produce eggs at all. And we could actually knock down the respiration components of those of this reproductive region, the vulva, and we can actually quantify how much of those parts contribute to the overall respiration. So this is kind of a stretch on that nanoelectrochemistry, and I'm taking the liberty because this is in a millimeter scale, but it's just to show that osteo populations and also organisms, more complex organisms, although the nematode is not that complex, they have different behaviors, they have heterogeneous behaviors, right, that you cannot assume they're homogeneous. And how that tie together with the nano aspects, that usually those experiments for respirations, they're done similar to cells, a petri dish full of animals that you just measure the concentration of oxygen over that petri dish. So we have an average respiration rate for the entire animal. But as the first instance, we can actually visualize and quantify the respiration of the different regions, and we can go that step further and is trying to deconvolve who is contributing more to the respiration. And that ties together a lot with the metabolism of the animal. Again, this cost of reproduction, and we can actually visualize that with those techniques. This is another image that Carla did as well with that animal. I think this is just a repeated slide that I forgot to delete, I'm sorry. And the last part, for the last 4 minutes or so, hopefully a little bit less, I want to talk about another implementation of SCCM. So we talk about a SCCM already, we talk about a SciCM, and we talk about SCCM for Carla's work with the sensing, but now we're going to talk about Marlene's work. Marlene's a current PhD at Warwick, and she actually uses SCCM to disturb. So similar to what Gus and Kelsey are doing of challenging the cells and see the distribution within the population. Now we're still doing oxygen reduction reaction on a platinum UME, but we're using a larger UME, and what we're doing is titrating out of solution that oxygen near a cell. So we approach this UME very near a cell. Instead of using it as a sensor, we actually are using the electrode to consume oxygen in solution and to pose a challenge into that cells. And here we're using BC12 cells because they're neuron-like cells. So we like that idea of investigating what, for instance, ischemic attack. So this kind of stroke that we can have can impact the cells and how they can impact differently. Those works, of course, they heavily rely on simulations. And again, it's the same thing I mentioned yesterday, and Guy has been mentioned the entire week, the powerfulness of simulation and how we should demystify that and how we can use that to not only correlate our experimental data, but on those cases, on those challenging cases, we can actually predict the experimental outcome before we do it. Well, not the experimental outcome, we can predict the challenge, and then we can see the experimental outcome because we're using our optical markers to visualize. So we're doing this in, I think, is a quite smart way. Instead of applying a cathodic potential just to reduce oxygen, we're actually doing galvanostatically. So we're applying a negative current. The currents here are just in positive values because we're just talking about reduction currents when I was writing the manuscript. But those are all negative currents, right? So those are reduction currents we're talking about. And the brilliance of this method is that if you apply fixed potential, the electrode surface changes with time, especially on biological materials. We have cell-produced proteins that can attach to material and can fall they can poison the electrode surface, and then you have a diminishing rate of reaction. By fixing the rate of reaction, remember that current is the speed of reaction. By doing galvanostatically, I'm actually fixing the rate of reaction. So the galvanostat is increasing the potential more and more cathodically to overcompensate the poison of the surface. So here we're actually titrating because we're fixing the rate of oxygen consumption. And those, of course, simulate data for different currents, how much a change in the oxygen concentration in a cell that's 30 microns away from a UME. And because we're doing oxygen reduction reaction, although we are in a buffer solution, we're also changing the pH, but you can see we're changing the pH by a amount that, although you can make an argument of 0.04, this might be biology relevant, and I assure you it's not. Like, this is within what the cell can buffer itself. This is within the error of most of the pH meter measurements and the media that we have found in literature anyway. So the nice thing we can do is, well, we can predict sort of the concentration change we're going to do with different currents, but we can use a hypoxia dye that fluoresces more and more if the cell is missing, if it has a hypoxic condition. And we can actually see this is not a healthy cell by a long stretch, but we can see that for different currents, I'm increasing the intensity, and I can plot the current, the fluorescence intensity here over time. And I can see there's a trend of current besides this outlier 7 nanoamps here. And the idea is that we can do this for a group of cells, and we can select group of cells. We have a healthy one, we have a very apoptotic one, and we have one that's barely going there apoptotic. So we can have this group, we can position our UME over here, and we can pose that challenge. Now we can apply current, and here apply, I think it was -7 nanoamps. And we can look at the normalized intensity of fluorescence over time. So those are just snapshots of the fluorescence density. And we can see that there is a trend here with cell 1, the challenge 1, has larger than cell 2, but cell 3 by far, which is almost equidistant to cell from cell 1 and cell 2, is the one that's actually suffering more of this hypoxia condition. We can resort to COMSOL again. This is a 3D model. It doesn't necessarily have to be, but a 3D model geometry allows us to do a little bit more stuff. And we can calculate the oxygen concentration prior to the experiment, because cells do respire normally, so there is a minor gradient, but after we impose a challenge, and we get here this graph, which is just the average concentration, you see that cell 2 and 3, they're pretty much seeing the same challenge. So why does cell 3 is seeing more of this hypoxia challenge? Well, it's pretty much because it's a apoptotic cell already. So its membrane is not intact. Doesn't have all its function properly. So it's not even fighting back this hypoxia challenge. It's just being a source of oxygen essentially to that UME. So that's one way we can look at those populations. And Martin has done that for a lot of cells. And of course, we have done a control experiments where we just approach the electrode, right? We don't do a challenge. And you can see that fluorescence barely changed for the group. But if we go to all the cells we challenge, they're definitely different from the control, but there's a very broad distribution. And again, this is just alluding to cells behave very different to each other. There's a few cells here that might be apoptotic, although we just try to look to the healthy ones here. But there is distribution. Cells don't behave the same. So you're having that petri dish full of cells and doing one experiment and assuming that that's the average behavior, it's not valid because they are different. And now we're moving towards, of course, using different markers to highlight those differences in cells, for instance, different metabolism of the cells, and see if we can correlate somehow with this spread in the behavior. And well, with that, I'd like to conclude, and I think I hammered that down quite a lot, that every material is heterogeneous, just depending on the length scale you're looking at. Right? So even if you go to atomic level of a single crystal kind of material, it's not going to be atomically flat, right? So it's going to be heterogeneous, at least in the topography. So everything is heterogeneous as long as you look with the proper length scale. It's important for us to understand those properties, especially if you want to design that material, the bottom-up approach, and if you tailor the properties. Also, it's a good thing to understand better the system. I think the ITO case is quite nice to make the assumption. And that we can use simulations for a lot of stuff, and that help us to understand and to not only predict what they're going to do this season, but actually understand and get quantifiable information. With that, I'd like to thank everyone who took part. As I said, I'm just a talking head. Most of the experiments are done by other people under my co-supervision. So Pat, definitely the boss that supervised me, and I have to thank him massively for a lot of stuff. Team Cell were the people that worked directly under me and did all the biology, and they're an amazing group of people. We have all these people that did all of the work here that I have to acknowledge, especially professors from biology, for the Canufs group as well, that had collaborated with us a lot, and Carla, Lisa, Fernanda, Mauro, and Felipe for the nematode work, which is an amazing work, and I quite like it, and they did a lot of it. I was just doing the simulations. And of course, the funding agency is another week, and this is my contact. And with that, I thank you guys for the attention, and sorry for rushing on this topic. Thank you.
Thank you, Gabriel, for the presentation. It's an amazing presentation with a lot of different results. I read the Nature Communications paper. It's fantastic. Congratulations for that.
Thank you.
And Bridget is saying thank you very much in the chat.
Oh, thank you. I appreciate that.
Someone have some questions until we go to the ending ceremony?
I have a question.
Okay.
In the ITO case you mentioned, and if I got it right, when you calculate those alpha values that you were considering, not only the half potential, but also the 1/4 potential and the 3/4 potential to compare the ITO with gold.
Yeah.
But you could see that there were changes when you go to ITO if compared to gold. And with this, you prove that the whole surface was active, but there was this change in 3/4 or 1/4 half potential. And
yes.
What would cause the change in these half potential? So you're considering it's active, but you're also showing that's not that active. May I assume it?
Yeah, so I think one of the things that we assume, and literature assume, that ITO is just like a metal, just like gold or platinum or something, so it should be as fast as it can be. But that's not the case, right? It's a semiconductor. It's a highly doped semiconductor, but it's not necessarily. So it's a surface that has intrinsic properties that is not that good of an electron transfer anyway, so it's going to take some time. It's a little bit odd that there's an outer sphere kind of reaction, so we shouldn't impact that much. But it's just showing that it's an increasing property. And we think it might be with the doping of the surface, to be fair. One thing that I didn't mention, because I think it would be complicated, is that we think there's an aspect of the fact that we're landing the pipette. The electric field is quite strong on that very tiny part, that we might change in somehow, that we might bending the band levels a little bit, and that skew the results. But I think that the take-home message is that it's not a metal, right? And there's no reason to be considered as a metal. That was highly doped, so it will have properties as a semiconductor does, and it's not that fast in electrokinetics. It changes a little bit.
Okay, so but should give the same current. You assume that if compared to gold, you said that the decrease in currents should not occur in a macro scale, and this was what you were looking for, if I got it right.
Yeah, that's an assumption that everyone does. So that's, if you go to literature, the assumption is that every metal should be as fast as it can be. A caveat of that is that maybe it's a technique we're using that cannot reach that level because of the mass transport rate. But it's compared to gold. So all this, and this is, those are brilliant work made by, especially from the front school of electrochemistry, which assumes that those islands are like they're as gold, they should be as gold. And the only explanation to this behavior is that the heterogeneous is active. Which honestly, as I said, I think is brilliant. It's just the fact that we cannot see the heterogeneous. But the surprising for us, it's hard to explain the alpha and the K0, is the fact that every single pixel we landed, we got a CV, right? Okay. And by this model, we landed a pixel that would be completely dead. We're not going to see. It could be the case that the things are not active in a smaller than 30 nanometer scale, which then has some discussion with mass transport that would make things more complicated. But that's an argument to be made.
Okay. Thanks.
Thank you.
Very nice presentation.
Thank you.
Thank you, Gabriel. We have a question. There is a question in the chat from Daniel Torres.
Can I reconstruct the microscopic response with many nanoscopic correlations? Yeah, it should be. So that's the thing that's bugging us a lot about the ITO, is that we can't. And that's why we think it's partially because we're impacting the ITO, the current distribution in ITO essentially, right? And especially because of semiconductor. But ideally, that should be an average, weighted average response of every single area. And that's what we show for the, I know there's a lot of slides, for the respiration, for instance, I know it's a different length scale, but if you go to the nematode, we could actually compare and see that was roughly the overall share people get from bulk experiments where they have, I don't know, 100 animals in a single petri dish indoor respiration measurements. It's essentially the average between all those areas of the animals they're looking to. So yeah, we should be able to reconstruct the microscopic from the nanoscopic behavior.
Thank you, Gabriel. The chat there's a lot of words saying thank you for you and for the presentation.
Yeah, I'm seeing, and guys, don't mind not having questions. We're all tired. And that's a very dense day. It's all good.
Thank you very much again to close with this beautiful lecture. And now we are moving for the last part, the ending ceremony. And until the ending ceremony, or in the ending ceremony, I would like to, as I mentioned by email for those that are here in the room meeting, Elsevier gave to us an ebook, and I would like until the end to do the raffle of the ebook, as I mentioned. It's here. Oh, the camera is not working again. It's now appear for you. It's appear. Yeah,
it's appearing.
I only need to wait for the computer to process all the information. We'll have the raffle of the ebook, and I will spin the wheel now, and there is 37 participants in the Zoom room, and I will try to do this first if my computer permits that. I will change the screen again. Now I will wait for the will appear for you. It's not appear yet.
No.
No.
It will appear.
It's shy.
Yeah. The computer is a little bit slow now, but it will appear. André is appearing now.
Yeah.
I may do the raffle if you want. Just jump.
Only waiting for. The computer is a little bit slow. Sorry for that. Oh, why?
Mauro, let's talk about Palmeiras in the meantime.
O Victor, você me está escutando?
We are the champs again.
It's appear for you or no?
Yes.
Yes.
Yes, it is.
Now it's
It's
appear.
spinning, I think. No. Yeah.
Now I think that now it's spinning. I will try to put to spin. Let me check if it's spinning properly. Now I will try to spin. It's spinning for you or not?
A little bit and then stop.
Okay. I will put now, and let's see what will happen.
Yeah.
Now we have a winner for the ebook. It's Katerina Tony. I will get all the information and I will send the information by Elsevier now, and Elsevier will send to you the ebook. Congratulations for that.
Congratulations, Katerina.
Congratulations.
And I will now try to close all the windows here and return for the ending part. Now I am appear for you. Oh, I would like, until the end, I would like to thank you all of the speakers and the attendants. I think that it was amazing week. I think that was possible for all of you to learn a little bit more about electrochemistry, try to know what we are doing here in Brazil and in the GIS lab. And it was an amazing week, as I mentioned. I would like to thank you very much for Mauro, for Vitor, Gabriel, André, for Metrohm to support, for Susana, for Roberto, and for Gui, for all the help with this process. It was a little bit difficult to manage all the stuff this week, but it was a very pleasure week to try to share some information with all of you. With this, until the other announcements, I would like only to do a advertise of the next school next year. I hope that we could do the school physically with the labs again and all of the exchange of information physically, not virtually. It was good to do this virtually, but I think that we can do that. We can return for the normal situation of the school. Okay, with this, I would like to thank you all of participants, all of the audience in the YouTube. I will now close the YouTube transmission, but all of you here in the Zoom room waiting, that I will need only to finish, and we will take a picture of a virtual picture of this school. Thank you very much for all of the attendance here in the Zoom and for in the YouTube. Thank you very much for all.
Thanks, Thiago, for the organization and for the